Berk lütfen bana bir şey söyler misin?
Ben bu arada kimseyi almıyorum. Herkes izinsiz giriyor. Öyle bir şey yok yani burada. Direkt giriyorlar. Ben hiçbir şekilde hiç kimseye izin vermedim şimdiye
Hadi
kadar.
ya.
Evet.
Aa.
Evet öyle.
Tamam, o zaman şeye bakayım. Ya Cem, anladın değil mi? Yani bir soru şey sıkıntısı olabilir. Haberin olsun. Yani ona hazırlıklı ol. Bir de senin gündeki hocalara sanırım çok fazla şey formunda gelmemiş soru. Cem, burada mısın? Cem burada değil yani. Ben şey yapacağım bu arada. Etkinlik ortasında dün e, yani düşüş yaşandığı için hiç aklımıza gelmedi ama hani etkinlik ortasında takvim davetiyesi gönderdi tekrardan. O yine hani deneyi 20 kişi falan arttırdı biraz ki ona bile hani 5 dakika kala attım yani. O yüzden ben ortasında tekrar bir davetiye göndereceğim kişinin artması için. Ama ben bugün çok aktif olmayacağım. O yüzden hani yani bir ama hani olur da Cem'de bir sıkıntı olursa moderatörlükte yani direkt birebir sunumları takip etmeyeceğim. Açıkçası çünkü çok beyin yakıyor ve hemen sonra. Yani birkaç sunum takip ediyorum ama şey Cem'de bir sıkıntı olursa bana da hani fark etmezsem ekstradan bana haber verirsiniz. Yani Cem düşerse ve vesaire gibi. Yine takip ediyor olacağım. Arkada maillerle mail göndermeye çalışacağım ben de. Takvim davetiyesi
Ecem canlı
göndereceğim.
yayındayız bu arada haberin olsun.
Merhaba. Okay, so let's wait for everyone to settle up. And hello everyone, and welcome back to the second day of QTalks organized by QSP. Today I will be your host, Cem Nurlu. I am the co-founder of QSP Bozbey and also member of QTalks. And today I will be moderating and sharing the speeches and your questions with the people that will be given. So before we start, for making some networks since we're online, I invite you all to write your current academic research interests or areas. So maybe you can find someone to talk with, your level of understanding and maybe what you're searching for. So all comments are appreciated and encouraged. And before we start, I will give some crucial information that was given also yesterday, but we will have to share this today also. So the first topic that we will be talking about is the issue of recordings and sharings. So all of these talks are recorded both on YouTube and Zoom. If the person that gives the speech gives us permission, we will be able to share them live on YouTube with you after the talks are over. However, they are not guaranteed, and the speaker holds the right to not give permission to share them. So we encourage you all to watch them live because you may not so afterwards. And we will also have to abide by code of conduct in the comment section and in general in QTalk. So our code of conduct for our QTalks are, our QTalk is dedicated to providing a harassment-free experience for everyone, regardless of gender, gender identity, and expression of age, sexual identity, disability, physical appearance, body size, race, ethnicity, religion or lack thereof, or technology choices. We do not tolerate harassment of event participants in any form. Event participants violating these rules may be sanctioned or expelled from the QTalk. If you are being harassed, notice that someone else is being harassed, or have any other concerns, please contact the organizers or moderators immediately. You can contact us through the social media or the mails that we have given you, or directly via the YouTube comment section. And also these talks will be awarded a certificate to the participants. So there was a total of 8 talks, and if you have filled out 4 of them, you will be given a certificate, but you have to keep an eye on the comment section for any new forms that you will have to fill. Please do not forget that your name, surname, and email must be identical in each one of them, or otherwise you may not receive one, since there will be a confusion. And let's move on to our event agenda for today. So today we will start with the talk of Batuhan, introducing us to QWorld, QTalks, and QSP and its team. Then we will move on to our first speaker, Dr. Bozbey, and then there will be a break after each talk, and we will move on to Dr. Denis Vasilyev. After that, we will move on to Michal Stechly from Zapata Computing, and we will finish our talks. We finish our speakers with Dr. David Lee from Academia Sinica, and there will be a final speech afterwards. So that's our agenda for today. So I will be leaving the floor to Batuhan for introducing us to the QWorld ecosystem.
Thank you, Cem. And let's start introducing. Hello, everyone. Welcome to this talk. I wish the talk to be good for you. And let me introduce to you about QWorld. QWorld is a global network of individuals, groups, and communities collaborating on education and implementation of quantum technologies and research activities. We work to popularize quantum technologies and quantum software and to involve more people in the field by working publicly academically, locally, internationally. QTalks is one of the QCuisines and the first quantum technologies community in Turkey. QSB7 is one of the student branches of QTalks. Now I want to introduce QSB7 team. My name is Batuhan Türk, and I am one of co-founder of QSB7, and also I'm physicist undergraduate students. This is Cem Nurlu. She is one of co-founder of QSB7 and representative. She is also physicist undergraduate students. One of our team members, Ali Mert Turaçlar. He is one of co-founder of QSB7 and social manager in our team, and also he is physicist undergraduate students. Another team member is Berk Doğan. He is one of co-founder of QSB7. Furthermore, he is mechanical engineering undergraduate students. One of our team members is Doğukan Köseoğlu. He is in our social media team, and he is electrical engineering undergraduate students. Mentor of our team is İpeknaz Oktay, and she is computer science undergraduate students. Other social media members in our team is Mehmet Kökçü, and he is Informed System and Technologies undergraduate students. The last person who I introduced is Menaf Kılıç, and he is one of co-founder of QSB7. Also, he is physicist undergraduate students. If you want more information about QSB7, you can follow us in social media, and now my friend is sharing social media accounts in comments box. Thank you for joining the talk.
Thank you, Batuhan.
You're welcome.
So before we move on to our direct first speaker, I want to introduce you to our dearest speaker, Dr. Ali Bozbey. Dr. Bozbey worked in the quantum engineering department of Nagoya University in Japan as a postdoctoral researcher. He is head of superconducting electronics group at TOBB, and his main research areas are superconducting devices and cryoelectronics. I want to welcome Dr. Ali Bozbey for coming. Sir, are you here?
Hello.
Hello. So Dr. Ali Bozbey will be giving us a speech on a single flux quantum logic, tackling the engineering challenges of quantum and neuromorphic computers. So before I leave the stage, I thank you for coming, and I'm leaving the Zoom to you.
Okay, shall I share my screen now?
Yeah, you can.
Okay. So thank you for organizing such a wonderful workshop, let's say. And then I am very pleased to be a part of this talk series also. Today I will talk about single flux quantum logic, which is supporting the technology for the quantum devices, quantum computers, and then how to tackle the engineering challenges of quantum and neuromorphic computers. Before I continue to the single flux quantum logic, I want to show my favorite slide, which is the previous technology forecasts about technology, computers especially. So in 1994, they forecasted that the computers will not weigh more than 1.5 tons. Actually, this was a correct.
Are you sharing your screen? Because we cannot see it right now.
Yes, you don't see my screen?
No.
Oh, sorry. Now is it okay?
Yes, it's okay.
Okay, sorry. Okay. So I was talking about some previous technology forecasts. In 1994, Popular Mechanics Journal predicted that computers will not weigh more than 1.5 tons. Actually, this was a correct forecast. Then in 1943, chairman of IBM, Thomas Watson, predicted that there's a world market for maybe 5 computers. Then in IBM again in 1968, for integrated circuit, they say, oh, what's it good for? Then Bill Gates told that they will never make a 32-bit operating system. In 93, they were making 16-bit operating systems. And then Ken Olsen predicted that there is no reason anyone would want a computer in their home. Then USA President Hayes predicted that landline phone would not be useful for anyone who would like to use it. So summary, when we are making some forecast about technology, I think we should be careful. These were maybe correct at that time, but now they look quite funny. So for today, established and emerging computer architectures can be classified in 3 groups. First is based on von Neumann architecture, which is all the processors actually at the moment today that we are using. Intel's, AMD's, ARM, even small microcontrollers are based on all this architecture. This architecture is efficient for number crunching applications. They make good mathematical operations and they make good deterministic operations actually. Then another architecture is neuromorphic architectures. This is emerging architecture and not yet in widespread use. Neuromorphic architectures are good for artificial intelligence algorithms, signal processing, basically fuzzy logic applications. They are good for. And recently, big players like Intel and IBM are getting involved in this type of processors as well. And then final architecture is quantum logics. So we have seen first demonstrations last year, we all know. And they are very efficient in very specific problems, especially for optimization, chemistry, or material search applications. And if we compare quantum bits versus classical bits, maybe the audience is already aware of this, but in the classical bits can get 2 different values only, just 0 or 1. So there is 1 possible permutation. But in the case of a quantum bit, we can have an overlay of different states called superposition. So in this Bloch sphere, we can have 2 to the power n permutations if we have n qubits. Then in this case, the advantage of this is exponential multiplication, exponential growth of capacity per qubit. So if in the case of classical system, if you have 10 bits, your capacity increases linearly by 2 to the power 10. But sorry, 10 times. But in the case of quantum bits, it grows exponentially. And if we compare neuromorphic and von Neumann architecture, in the von Neumann architecture, we have arithmetic logic units, memory, registers, cache, etc., blocks, computer blocks. But in the neuromorphic architecture, we have mainly neurons and synapses. And then we don't have cache or memory, RAM, etc. So I will talk about this in detail later. If we see the progression of the computers, maybe you know this ENIAC, electronic numerical integrator and computer. This was the size of a room and the weight was about 30 tons. Then after 25 years, the first, we can say, the microprocessor Intel 4004 was introduced. And then now we all know this Intel's AMD microprocessors are now very widespread use. So the progression is enormous, unbelievable. Now, today, I think the quantum computers are going to face the same progression, but we don't know when and which technology. For example, in this case, ENIAC had vacuum tubes. So each tube was like few centimeters. Now we have transistors of nanometers. So here we see that the size is like old ENIAC, and it has 100 qubits. And I am very curious when we will able to see 1 million qubits in the size of a palm. I mean, small size quantum computer. I'm very curious if we will be able to see it or not. So many groups are working on the control and measurement of the qubits. So I will talk about superconducting qubits. There are alternative technologies that were presented yesterday or today will be presented, but I focus on the superconducting qubits. So superconducting qubits, especially transmons, are now very robust, very high coherence times, etc. But still they need cables for controlling and reading out the states. So control and measurement is done, maybe classified in two ways. One is using conventional room temperature electronics, such as microwave sources, pulse-shaped signals, and DC signals. And then other way is to use cryoelectronics at 10 millikelvin or 4 Kelvin. And in this case, we can also classify them in two groups. In one group, the control and measurement is done with cryoelectronics, but the electronics just replicates the room temperature electronics. So they make microwave sources or measurement tools in the cold stage, but still the principle is very similar to room temperature electronics. Another way is to use the inherent superconducting technology methods, like single flux quantum pulses or Josephson photon counters for readout. So the details can be studied in these references that I will show in the last slide. So the problem with the room temperature electronics is, I mean, so you have to connect them. You have to connect them to qubits. Then you need thousands of cables reaching to the millikelvin stage. I mean, for hundreds of qubits, maybe it's possible, but for thousands or even for millions, this is not possible. In the case of cryoelectronics located at 4 Kelvin, we need fewer cables. So this makes it more feasible to scale up the number of qubits. And if we divide one more, this control and measurement electronics based on technology, so CMOS and single flux quantum. In the CMOS technology, the electronics is placed in the cold stage at 4 Kelvin by replicating the conventional RF components here. In the single flux quantum technology, some Josephson arbitrary waveform synthesizers can be used to generate the control signals, or Josephson counters can be used to read out. But I think one of the novel methods is to use the inherent superconducting technology methods. Here it's proposed by Mukonov and Lee, and first feasibility demonstrations are done. They use a quantum classical interface at the cold stage, and then use SFQ processors and coprocessors at the 3 Kelvin stage or less other stages to control the quantum bits. So these two methods are based on single flux quantum logic. I will briefly explain principles of single flux quantum logic now. So we know that superconductivity is also called microscopic quantum phenomena. It means there's a wave function associated with a superconductor regardless of its size. So in the normal metals or semiconductors, normal electrons are disordered. So they collide with each other while transferring electricity, while moving inside the crystal. But in the superconductor, super electrons are ordered. It's like a moving high-speed cars in an autobahn or marching soldiers. So they move in harmony. It's because there exists a macroscopic quantum wave function that describes the behavior of the entire super electrons in a superconductor. So entire super electrons in a superconductor act like a single electron with one wave function. So we also say that superconductors are like artificial atoms. And if there is a ring made of superconductor, I mean, when there's a hole inside the superconductor, the phase of the wave function must follow certain rules. So this rule is, with a complete turn of the ring, the phase value needs to go back to the same value. So it has to be continuous. It cannot have discontinuous value like this. So this is only possible if the flux penetrating the ring is quantized. It means the flux penetrating the superconducting ring can only get integer multiples of a flux quantum, which is equal to 2.07 times 10 to the minus 15 Weber. So the name of single flux quantum logic comes from this flux quanta. We manipulate this flux quanta in the logic circuits. So the presence of the flux quanta in the cell means logic 1. If there is no flux quanta, it's logic 0. Another fundamental device is the Josephson junction in the superconducting electronics, which is basically two superconducting material separated with a thin barrier from each other. They have two wave, each has wave function psi1 and psi2, and they have to satisfy the linearly coupled Schrödinger equations like this. If we solve this coupled Schrödinger equations, we find the AC and DC Josephson equations. So first, this was discovered by Brian Josephson during his PhD. Then he got the Nobel Prize. He is one of the youngest physicists to get the Nobel Prize. So based on these equations, Josephson equations, the IV characteristics of the Josephson junction can be obtained. So I don't want to go into details, but if the Josephson junction is an overdamped junction, it has a one-to-one relation between the current and voltage. So we use overdamped junctions in SFQ logic. To use it as a logic gate, we should form a junction, Josephson junction inductor and Josephson junction loop like this here, and then bias the junctions with some DC current. When the junctions are biased just below their critical current, so we are ready for the logic operation. So when there's an SFQ pulse or any disturbance coming from the input side, for example here A, then temporarily the junction switch and then go to voltage state. I repeat it again. So when the junction switch and go to voltage state, in this loop, there is a two phase shift. So 2p phase shift. When there is a 2p phase shift, so the flux quantization rule is not destroyed. Just the number of fluxons is increased or decreased in the loop. Then one flux quanta is released here. So this is one very basic gate. We call it Josephson transmission line. It means it's used to transfer the one flux quanta from one point to another point. Similarly, this will trigger the next junction, and then it will proceed. The flux quanta, single flux quantum amplitude is few hundred microvolt. It's less than 1 millivolt, and the pulse width is about 2 picosecond. We can split one flux quanta by using a splitter, for example. Similarly, we get we switch these two junctions, and then we start with one pulse and we get two. So I skip the rest of the circuits, but in principle, it's possible to make almost all the analogs of CMOS logic gates, like memory cells, flip-flops, T flip-flop, D flip-flop, AND gate, OR gate, etc. So this logic definition was proposed by Konstantin Likarev in 1992. So please see this paper for the details. And the problem is, so since the pulse width is just 2 picoseconds, how can we use it in our logic circuits? It's too short to synchronize and to measure. So in this case, the logic gates, most of the logic gates have a clock. Here we have a setup time and hold time, and in between there is a useful time. So between this, in this useful time, if there is an SFQ pulse, then it's logic 1. If there is no logic SFQ pulse, then it's logic 0. We can adjust this useful time as much as we like. Another important thing is to interface this with semiconductor logic circuits. We need to convert this pulse logic definition to voltage state definition, because CMOS circuits work with voltage state logic. For this purpose, DC SFQ and SFQ DC component cells are developed. In this case, if there is a rising edge in the DC SFQ circuit, then we generate an SFQ pulse. And for the output part, if we had an SFQ pulse, then output is toggled. Then we can switch. We switch to CMOS compatible logic. For example, this is an OR gate measured in our laboratory. Let's say this is the first line is clock. So between these two clocks, I mean, clock is two rising edges given by CMOS clock generator. In between these two rising edges, we don't have any input. So it's 0. So 0 or 0 is 0. Then in this period, we have input B is 1. Then 0 or 1 is 1. And 1 or 0 is 1. And 1 or 1 is 1. So we can adjust this period as much as we like. It can go up to tens of gigahertz, or it can go down to kilohertz. It depends on our capability of room temperature electronics. And another advantage of SFQ logic is it's compatible with available infrastructure. I mean, we design the circuits by using commercial VLSI tools, and then get foundry service by using commercial foundries, and then measure them by using standard room temperature electronics. This is very advantageous in terms of developing complicated circuits. Now, if we go back to where we left, by using this SFQ logic, then we can implement many circuits. I mean, I can say almost any circuit that can be implemented by using CMOS, any logic circuit mainly, can be also implemented by using SFQ logic. So, for example, this is a Josephson arbitrary waveform synthesizers. It's called JAWS. In this case, if we stack squids on top of each other, and then we use splitters, I explained in the previous slides. You have one pulse coming from the lookup table of patterns. Any whatever waveform you want to synthesize, you need to define it in the lookup table here and store in the memory of the circuit. And then, depending on how much amplitude you want in the qubit, you can stack Josephson amplifiers, squid amplifiers, squid multipliers here. Then you can send these pulses or waveform to qubit to excite or read out the qubits. For example, in this one is a ROM, read-only memory cell, that can be used to store waveform patterns. And this is a voltage multiplier cell. It was developed by Sasan, and this was developed by Yasemin. And another arbitrary waveform synthesizer is demonstrated by Sirius in 2020, recently. They also use a Josephson array to synthesize an arbitrary waveform to control a transpond qubit. So for details, you can see this paper also. And another method is to use the inherent properties of SFQ logic. So you are maybe familiar with this Bloch sphere of qubit state vector trajectory. If we have a trajectory here, and then if we want to change the state, then we can use SFQ pulses. So by using little pulses, we can move the trajectory in the Bloch sphere. So this is just exaggeration, of course. In one pulse, you cannot move such a trajectory, but Leonard demonstrated that, and Lieberman proposed, and Leonard demonstrated that it's possible to move on the Bloch sphere by using such an approach. And one very important property is they are fabricated on the same chip. So the control electronics and the qubit can be fabricated on the same chip. And then, since it's digital, it's possible to interface with SFQ-based microprocessors. So you don't need to go up to room temperature except for interfacing. For controlling and reading out can be done all at 4 Kelvin stage by using SFQ logic. So quantum computers with thousands or even millions of qubits will require a scalable solution for qubit control and readout electronics. And I think if we will use millikelvin qubits, then control electronics should also be compatible with cryogenic temperatures. So it can be either CMOS or SFQ. So some groups are focused on SFQ logic, some groups are focused on cryo CMOS. But I think it's not feasible to use room temperature electronics beyond some number of qubits. So time will show which one will be more promising. These are some circuits that was implemented in our group. So they were not intended to use with interfacing qubits, but basic building blocks can be used for controlling qubits that I will show, for example, later in one of our circuits. So I now switch to neuromorphic computing. Neuromorphic computing is based on mimicking biological neurons, basically. So if this is a biological neuron, it has a soma part, it has dendrites, axons. So based on the threshold values and synaptic weights, pulses are generated in biological neurons. Since the SFQ logic is also pulse nature, it makes an ideal candidate for neuromorphic architectures. So we can utilize the biological neuron methodologies to superconducting neuromorphic architectures. Both is based on quantized spiking neural networks. An artificial neural network design means we have some neurons, then these neurons are connected to each other, and training means which neuron is connected to which neuron and what are the weights of each connection. For example, in this case, this hidden layer first neuron is connected to output layer with weight 2, for example, and then it is connected to Y2 by using -2, etc. So designing a neural network means finding the connections and finding the weights. Then for this purpose, first we have to have a neuron with a synapse, soma, axon, and dendrites. First, we try to design a soma. Soma is the decisive part of the neuron. It means if the threshold is exceeded, then it gives an output. For example, here, now there is no current in the loop, let's say, and then we sent one SFQ pulse. Then we excite a current here, but different from the Josephson transmission line that I showed before, there is a resistance here. So it means it's dissipating loop. So when there is a SFQ pulse coming here, and if the threshold is not achieved, here is the threshold in this here red line. So when we have one pulse only, the threshold is not achieved. So we don't have any output here. But if we have consecutive pulses like this, then after the third pulse, we will exit the threshold here. So in the first one, we could not. Second one was very close, but it did not exit. And then in the third pulse, now we have exit the threshold. So we have a SFQ pulse. It means this neuron, this soma, has a threshold of 3. By adjusting these circuit parameters, we can program the threshold of the neuron. For example, this is a fabricated neuron and experiment results. This has a threshold of 2 and this has threshold of 3. And they operate correctly. Another part of the neuron was, now we show soma, and another important part was synapse, where the interneural connections are achieved and weighting is also achieved in the soma. So how can we do it? By using this squid multiplier. Maybe you remember this from the arbitrary waveform generator. So the good part of this logic cells is they are mostly general purpose and can be used in many other places. In this case, we use this as a synaptic weighting cell. For example, if we, in this case, this is multiplication by 4, but then you give one pulse here, and then you get 4 pulses. So you multiply it by 4. But if we disable 2 of them, then you can get 2. Then you get weight of 2. how can we enable or disable this each squid? We can use a switch here in this part. If we open the switch, then there will not be any current flowing this line, and then current will not be coupled. So we will not have any output. So by opening and closing these switches connected to this squid loops, then we can program the neuron synaptic weights. Then now we have a programmable synapse here, but for a useful synapse, it should also be able to handle negative weights. Then how can we achieve it? If we replicate these synapses, same one twice, and then use one of them as positive weights and another one for negative weights, and then sum them at one point here. So the current generated from the positive side will generate a current towards the right side, and then from the negative synapses, it will come from right to left. At this node, there will be a subtraction. So then if we couple the subtracted net current, we can then implement subtraction in the weights. So for example, in this case, if we, now please remember, the number of switches that are closed determine the weight. So if we have 4 switches here closed, then we have weight 4 here, 1 here, 1 here. So on the positive side, we have plus 6, and on the negative side, we have minus 4. So the net weight from this synapse is 2. Then if you provide these inputs, you should expect 2 pulses from here. Then if you use a soma, such a soma with 2 thresholds, then you can implement this neuron by using such an approach. Then we have 2 pulses here, and threshold is 2. So we expect 1 output from the soma. Then we tried this for different combinations of inputs and weights. Then for any combination, we could achieve successful operation. Then now we have a neuron, programmable neuron. So we try to see this in a public data set. In the artificial intelligence neural network communities, there are some benchmark data sets. And one of the simplest is this iris flower data set. It has 3 classes: iris setosa, iris versicolor, and iris virginica flower types. So it has 3 outputs. Class is 3 outputs, and it has 4 inputs: sepal length and sepal width, petal length and petal width. So if we train by using this 50 instances, I mean 150 instances, then we can design this neural network. It means we can find the number of neurons, neuron thresholds, and then interneuron synaptic weights. Then we found these weights. So next step is, after we find these weights, we can implement it by using the soma, the neuron architecture that I showed you before. So for example, in this case, weights are 2, 1, minus 1, 1. Then you just program the switches based on these weights. And then you give the inputs here. Then when we simulated this implementation, circuit implementation, we could get about 95% success rate. So we could not yet verify this experimentally, but we are positive. We hope it will be able to work in experiment also. So in simulation, it works now at the moment. So to scale up this neuromorphic architecture, one possible way is to use SFQ chip for the soma and synapses, and then use a CMOS chip as a switch for the switches, because since these switches will be static after the training stage, then the CMOS power consumption will be negligible, and then it will not have any problem. So the switches are going to be used to control the neuromorphic SFQ chip. Then by using this multi-core approach, it can be scaled up. So Zhu 2020 reported this plot for neuromorphic processors. For example, this True North is IBM's architecture, and then we added this, overlaid our approach here, SFQ-based approach here, by using different SFQ technologies. So RSFQ is what I explained now. eRSFQ is energy efficient RSFQ, and AQFP is another SFQ technology based on adiabatic logic. So we see that when we calculate the power consumption and computation power, it's one of the most promising technologies for achieving neuromorphic processors. So my dream, or maybe most of the researchers' dream, is to create an hybrid high-performance computer that can decide to use which architecture to use depending on the problem. So if you have a number crunching problem, the HPC uses Von core. Another problem is maybe suitable for neuromorphic part, and then maybe another optimization problem is suitable for quantum. So this part should be transparent to the user in the future, I think. So the user should not be caring about which architecture should he use or she use. Maybe she is only interested in the solution. And I hope we will be able to see this in some near future. Thank you. And these are the references that you can see. Thank you.
Thank you for this great speech. I believe that you have piqued the interest of everyone by giving us a speech on a hot topic in today's quantum computing, hyperword computing, and artificial neural networks. So if you have time, there are a few questions that came from our listeners, and some from mine also.
Yeah, please.
So yeah, you have talked about the advantages of SFQ logic over CMOS, and as far as I know, SFQ is only low thermal radiation used, but CMOS can be used in room temperature. So how does this affect the disturbances or control readout errors in transmon quantum computing, or does it affect, does the effects of thermal noise be better in the SFQ rather than CMOS?
Yeah, CMOS is in classical design methodology is intended for room temperature, but now very low power and very high performance cryo circuits are also being developed. So CMOS is also compatible with cryogenic temperatures now. So sub-threshold circuits or even less high technology nodes, they can operate at 4 kelvins now. So there is no problem in operating the CMOS circuits at 4 Kelvin. And amazingly, they can compete with SFQ logic in terms of power consumption. I mean, so much advanced. CMOS is the workhorse logic, so it's not easy to compete with CMOS logic. and they can develop cryo circuits, very reliable circuits. So for this, please see this paper. It's a very recent paper. They could implement all these blocks in 4 Kelvin. Also, IBM's approach is also based on cryo-CMOS. So yeah, CMOS is advanced now in terms of cryogenic operation.
Okay, thank you. So another question is also related to this one. So we talked about SFQ powered controlled quantum computers, or qubits rather. So does it have any metrics that we can compare with the other methods like qubit error rate or disadvantages to the cryo-CMOS or qubit capacity?
Yes. So now I cannot give any numbers from my mind, but I recommend to maybe see these papers. They also compare with conventional methods, their performances. So they look promising, but I don't know numbers at the moment. But I recommend you see these papers for numbers.
Thank you. So another question is about the SOMA architecture. So are the weights in the SOMA architecture adjustable on the go, or is it determined in the manufacturing process?
That's a very good question, I think. It's adjustable runtime on the runtime because it's controlled by these switches. And those switches are in the CMOS chip. So CMOS chip can be programmed in serially. So you can just program it in serial manner, and then each switch can turn on and off, then it can operate. And synapses can be programmable this way. But SOMA is not programmable. I mean, SOMA itself is not programmable because it's based on the time constant of this LR in the loop. But one method to use is, where is it? Okay, here. We call it M-SOMA, means multi-SOMA. It is programmable. This M-SOMA includes more than one SOMA circuits, like thresholds from 1 to 5 or 1 to 6. So by biasing anyone that you like, then you can program the SOMA. So in this JJM SOMA circuit, there are many SOMA circuits with different thresholds. And then by using this bias current, still again controlled by CMOS circuit, you can also adjust the weight of threshold of the SOMA.
So thank you. So also I have another question. So it is a synapse-like structure from what I understand. So is it possible to have an arbitrary topology on the go, or is there a construction that is possible to change the topology the way you want, or disable and enable some of them? And also another question related to the last one is that since SFQs weights are adjustable on the go, does that mean that we can do some SFQ logic to do some backpropagation and train on the runtime, or do we have to use a hybrid method for that?
Yes, those are really good questions. Our goal is to achieve all these questions, problems, but the problem is then the network should be fully connected. For example, if we have 1,000 neurons, let's say, 1,000 neurons should be fully connected to be programmable as much as we like. I am not sure if that is a feasible goal or not, but maybe up to hundreds of neurons fully connected can be possible. But after some numbers, so for example, in this case, let's say we have 4 cores. These cores can be fully connected inside, but not fully connected between each other. Is it clear? So then,
I believe so.
Then the neural network training algorithm should be developed to take care of this.
So thank you. And another question is about one of my interests, actually. So in places like CERN, to record the data from the collisions, they need a really high-speed triggering mechanism and analyzing mechanism. And currently they're trying to work with some hardware-level neural networks.
Yeah.
However, this seems also promising. So does the SFQ powered neuromorphic chips is a possible usage in such triggering analyzing methods?
Yes, yes. I think one of the most suitable applications of such a device is maybe in this CERN's signature search. But the data is huge in CERN's output. So before we test it at CERN's data, I think the circuit should be scaled. But the short answer is yes, we want to, and we will be like to try it there. But first, we should be able to scale up the circuit. Maybe thousands of neurons.
Thank you. So I think that is all for the questions that we have. So I thank you again for coming and giving this such amazing speech. I think it was really interesting and promising.
Thank you. It was a pleasure for me also. Thank you.
Thank you for coming. So we will give a small break and then we will move on to our next speaker after the break. So goodbye everyone and thanks for coming to this one.
'Cause we be on a top. Oh, we feeling falling, falling, 'cause you know tough love. Oh, we feeling so high. Don't be afraid of falling, feeling so falling, 'cause you know we gon' fly. 'Cause we be on a top love.
Hello, everyone, and welcome to our event again after a break. There was a little problem about our moderator, so I'm going to continue for now. So let me introduce you to our next speaker. Our speaker is Dr. Denis Vasilyev from Institute of Quantum Optics and Quantum Information. Dr. Vasilyev is working as a postdoctoral researcher at Quantum Optics and Information Group led by Professor Dr. Peter Zoller. His main research interests include quantum measurements, quantum simulators, and sensors. So, hello, Dr. Vasilyev. Thank you so much for accepting our invitation.
Hello, and thank you very much. It's my pleasure.
Great. So, I think we have like the same time zones, right? It's like 12 or 12 a.m. or something like that for you, right?
For me, it's 1:20, 1 p.m.
Well, that's pretty good. Only 1 hour.
Yeah.
Great. So, Dr. Vasilyev, I want to ask you that, like, how this pandemic affect your work? I mean, can you give us like how it affected, like all these things moved to on the internet? So, how would you describe all this whole year under this pandemic condition?
Well, one can certainly attend much more conferences at the same amount of time. So in some sense, it's even convenient.
Exactly. Like we got the chance to host you right now. It's a great pleasure. I mean, it's a great opportunity for us, for example. So, if you're ready, I think we can start your presentation.
Okay, very good. So when I start sharing this screen,
okay. A little reminder, by the way, for our participants, please feel free to ask any questions during Dr. Vasilyev's presentations. And also you can make discussions and conversations from the comment box. Please feel free to do that too. And at the end of his presentation, the questions will be directed by me to our speaker. So good luck. Dr.
Okay, very good. Can you see my screen?
Yes, we can.
Okay, very good. Thank you. My talk will be about the quantum variational optimization in quantum metrology, in field of quantum metrology and quantum simulators. So I'm going to tell you how we would like to build a programmable quantum sensor. So the work is done mainly here in Innsbruck, in our institute IQOQI, together with the group of Rainer Blatt and Thomas Mons here in the university also, who are doing the experiment now. So I'm going to tell you about the theory and a little bit about the experiment, as I am the theorist. So let me first show you where I am, where my talk is situated with respect to the quantum technology landscape, as I can see it. There are quantum computers, like digital quantum computers, and quantum simulators, which are kind of a bit quite different devices, similar devices. They're doing a bit different physics. With quantum simulators, we really want to simulate many body dynamics. Then there are quantum communications, which is quite different, but it's already kind of used a lot in the real field. And then there is a big topic of or field of quantum sensing and quantum metrology. Today I'm going to talk actually about both of these two fields, quantum sensors and quantum simulators, which we are going to merge together using the variational quantum algorithms with the aim to build a programmable quantum sensor, thus reaching like the optimal meteorological device. So that's a brief overview of my talk. And first I'll tell you about why the what quantum sensors and quantum simulators do have in common. So as an example of quantum sensor, I show you here the results of the improvement of the optical atomic clocks in recent years. So I think currently the standard of time is defined by the cesium clock, and that's these blue points improving up to now 10 to minus 15. And quite recently, the optical atomic clock started to be developed, and now they overtook the cesium clocks and to work in the regime of 10 to minus 18, and soon very much possible to -18 stability. And these clocks are made of atoms. These are the atoms in atomic lattice. These are containing thousands of atoms. Or it actually could be just a couple or one or two ions in an ion trap. And quite recent development is actually using a few several atoms in a tweezer array, which are also very well controlled and can perform on a competitive level with these two platforms. And if we look at the platform for quantum simulators, which are used to simulate quantum dynamics, many-body physics, these are essentially the same devices. These are ions trapped in a ion trap, optical atoms in optical lattices, Rydberg atoms, or there are some other devices. So what they have in common, these two platforms, they are essentially, sometimes they are the same devices, they just use differently. And the common thing between them is that these are very well controlled devices or quantum systems. However, they have a limited set of available quantum operations. So usually they are not suitable for digital quantum computers. And well, that's not a problem for atomic clocks, obviously, and for simulators. And we're going to use this common what we have between these devices and build the best possible quantum sensor, or programmable quantum sensor. But so first, let me tell you a little bit about quantum metrology within one slide. So in the quantum metrology, the problem is stated in the following way. We have some input state, rho in, somebody prepares it, and then there is some process, maybe unit Hamiltonian dynamics, maybe some dissipative process, which encodes a classical parameter, a phase, into the state. So the state evolves under some dynamics such that it got this phi index. And then after that, we perform the general measurement on the obtained state. And the goal is to actually estimate the phase encoded during this free evolution based on the measurement and best estimator we have. So, and there are like two big or different views on this problem. One way is to look at the problem from the quantum Fisher information approach, where we assume that our estimator is a locally unbiased estimator. It means that when we got a measurement outcome, then we plug into our estimator function, and if we average over all measurement outcomes, then on average the estimator is equal to the true phase. It means that then the only quantity which characterizes the performance of such a device is actually the variance of the estimators. It's on average it's always correct or locally correct. Then we can just estimate the variance of the estimator, and it gives us the precision. And there are some fundamental limits on what the precision we can get. Which are given by the Fisher information. These are some quantity which can be calculated, and importantly, it depends only on the initial state. So it's kind of optimized all possible measurements. And that gives rise to the so-called Heisenberg limit, where n is the number of particles participating in the dynamics. Another approach is a Bayesian approach. Here we do not consider an unbiased estimator. Here the main point is that we assume that we have some prior information about the quantity we want to measure the phase. So it has some distribution, a Gaussian distribution or something else. And then when we perform this measurement, we use some estimator which is not necessarily biased. So just some estimator, and then we calculate the mean square error and characterize the whole measurement procedure with this averaged mean square estimator, so with the bias mean square error. And there are also some limits on this error, and And that's what we are going to use. So a good quantum sensor should have a small Bayesian mean square error. Well, there is some difference with these two approaches, and but in the following we are going to talk about this Bayesian phase estimation because well, it's a bit more complicated. Technically, numerically, it's harder to find this optimality, but it provides an attainable limit. So if we solve this problem, we found a good initial state and good measurement, then we know for sure that it can be done. If the Fisher information is a bit more tricky, so sometimes you can be over-optimistic, you can get over-optimistic results with it. So and another kind of why do we use Bayesian phase estimation can be shown directly with the atomic clock. That's a picture of the atomic clock, or my simple understanding of it. So essentially, atomic clock is it's a laser. It's a very good laser with optical frequency fluctuating somehow, and the goal is to use the atomic cloud with some atomic transition with frequency omega A, which is more stable than the laser. And then we can compare these two frequencies by measuring the phase difference between them and stabilize the laser. So that's what optical atomic clock is. It's a way to stabilize laser better than it's built. And in order to do it, one has to measure this phase. So the phase which occurred during the evolution, so which encodes the difference between the laser frequency and the stable atomic frequency. And here, I, for example, show these trajectories for the phase difference, and you can see that they kind of distributed approximately. They are distributing according to Gaussian distribution, and this is with a very high precision. So that's why we kind of can assume that if if we start from some known initial phase and then we evolve for some time t, Ramsey time, then afterwards we have an unknown phase which we want to measure, which is distributed by Gaussian distribution. That's how it fits naturally into this Bayesian framework. So the conclusion is that in order to build a clock, you have to measure phase. And how do we measure phase? It's done with the use of Ramsey interferometry. Here, that's the circuit. We start with our atoms prepared in all spin down state, and then we apply pi over 2 rotation around the y-axis. This generates all spins pointing sideways. So here I show a Wigner function of the state. So and the prepared state is kind of all spins are pointing towards us here to the equator. That's why it's blue. And then after the state preparation happens the free evolution, which encodes now the phase into the state. So the phase phi is encoded such that essentially the evolution is very simple, it's just rotation of the spin. So the collective spin is rotated. We see now that it's slightly shifted. And now happens the third stage where we perform measurement. And these are the measurement results for these two different states. We see that the M, the measurement outcome, so the projection of the state onto the quantization axis, is quite different for these two states, and that's what we use to estimate this phi, so the angle up to which it is rotated. And of course, how well we can do it, it depends on the state itself, because this distribution, the width of this distribution depends on the initial state. One could use something like what is called squeeze state with a bone narrow distribution, and also do something about the measurement procedure such that these two states are essentially more distinguishable. So I'll talk later a bit in more details what does it mean that it is more distinguishable. So how can we improve this standard Ramsey interferometry with uncorrelated states? We can go to a correlated state or generalized Ramsey interferometry, where after initial state preparation with false spin down, we introduce some general entangling unitary U and N shown here. And then the same free evolution happens. We cannot do anything about it. It encodes phase. And after that, we introduce a general decoding unitary, followed by the standard measurement. And this approach incorporates metrological problem in full generality. So what one can encode by applying the entangler, you can encode any input state, and by applying the decoder to some measurement, you can encode arbitrary measurement. Therefore, it incorporates all previously known results on spin squeezed interferometry or generalized measurement interferometry, and that's what we are going to consider here. So again, let me remind you how the Bayesian approach works here. We start with the prior distribution, P of phi, and after the measurement, we get some measurement outcome. We basically have to multiply the prior distribution by the conditional distribution of the measurement outcomes, and it gives us new posterior phase distribution. It's a more narrow distribution. We learned something about the phase, so the distribution is more narrow. So, and how narrow it is quantified by the mean square error. So that's our figure of merit for the quality of the estimation of the phase, where this conditional probability is essentially given by the initial state, which is like evolved by the encoder, free evolution, decoder, and the measurement outcome. So that's the quantum mechanical probability describing the whole measurement outcome for any input state phi. And then the cost function which we adopt is this Bayesian mean square error. So for each phi, we average this error for each possible input phi, just integrating it with the prior distribution, where the prior could be Gaussian, so we will consider Gaussian, and it could be general. And then the problem is to minimize this cost function. So one has to minimize it by optimizing over this general unitary decoder, entangler, and decoder. And surprisingly, this problem can be solved efficiently, at least numerically. It is solved quite recently. But of course, it provides you some unitaries which are kind of arbitrarily complex. And the problem is how to actually prepare or how to realize these unitaries to make this approach work. And here comes in the variational approach which was introduced in quantum simulators first, I think. So in this variational approach to quantum problem, where we have a quantum device which can do some circuits, well, available to out of the available gates. It doesn't have to be a complete set of gates. Whatever is available on the platform is good. And then there is a feedback loop. So we perform some circuits, we perform measurement, somehow use the classical computer to feed back result to the quantum circuits, and just running this feedback loop, we can achieve a desired result. And what is the desired result is encoded in the cost function. So we have to minimize the cost function. We somehow have to encode our problem, our interesting problem, in the cost function and the variational parameters, which kind of tune these gates. And one of the examples is, for example, preparing a ground state of a many-body Hamiltonian. So there is a complicated Hamiltonian with some interacting coefficients, and then we can measure the expectation value of this Hamiltonian by just measuring correlation functions. And by varying these variational parameters, we can minimize it. Thus, it means if we find the minimum, then it means that we found, we've prepared the ground state of the Hamiltonian. And there was recently an experimental work on exactly this topic. So now we want to use the same approach to the quantum metrology, where we just take a different cost function, which encodes the problem of interesting to metrology, to the kind of precise measurement of the phase. So for this general circuit, we have our estimator. Estimator we consider just a linear function of the measurement outcome m, and here we plot a mean value of the estimator. So for the coherent spin state, it will be just a sine function. For the squeeze state, it also will be the same sine function. And the optimal, so if we optimize, we find the optimal entangular encoder, then that's the result is given by the dashed line. You see that it's in much longer, wider range of phase. It's a linear function, which is convenient, which is good for us because it's then our measurement gives us directly the phase. And the error, so the deviation of the estimator from the true phi is shown here. So that's for the coherent spin state. For the squeeze state, we have a smaller error with a little bit also more narrow bandwidth. But the optimal interferometer allows us to actually achieve wide dynamic range with low noise. And that's our goal, to approach this black line with a real device. So we introduce again this Bayesian mean square error, where we average the actual mean square error over prior distribution, which in our case is a Gaussian distribution. And then comes in the variational ansatz. So we consider a certain case. In particular, we consider the global rotation and one-axis twisting case. So the global rotation is just evolution under the J, or one of the collective spin components, J, Z, let's say. So it's just a rotation. And one-axis twisting is it's a nonlinear operation, which, it basically twists your state if you start from a coherent spin state. And these basic operations, they are available on a wide range of platforms, in crystals, in atoms, in a resonator, in PC cloud, and we can also. So it's not necessary to use exactly these gates. We took them just because that's what happens in real devices where clocks are working, and that's what we have in experiment here. We can also use it with another type of available interactions, namely finite range interaction. I'll have a slide later about it. How does it work? So in order to make this variational approach work, we have to decompose our desired encoder and encoding unitary into the layers. Each contains these operations, some combinations. So we have twisting around z-axis, twisting around x-axis, and rotation around x-axis. And then we just repeat these layers many times. Well, not many. It depends. We will try 1, 2, 3 layers. And then there are these angles of twisting and rotation. They encode these are our variational parameters. And the decoder, we essentially do similar thing, also layer of twisting and rotation. It has its own twisting and rotation angles, and maybe different number of layers. And so this decoder basically encodes this generalized measurement operator M, which we effectively achieve by applying it. So now the goal is to minimize this cost function, where that's our error. So that's the estimator AM, phi true phase, and the conditional cost function conditioned on our variational parameters theta and theta. And so that's the result of the optimization. So we just try with different number of layers. So we encode the complexity of the circuit as 2 numbers: number of layers for encoder and number of layers for decoder. So that therefore 0, 0 means the standard classical Ramsey interferometry with uncorrelated states. So we don't do anything with spins. We just prepare we apply this pi over 2 rotation, then perform measurement of effective measurement of jy component. And this purple line shows us the limit of the classical interferometer. So everything above can be done in a classical device. Now the next step is to use one layer for encoder. This way we can prepare an interesting initial state, which is more optimal. And in this case, you can see that the orange line is substantially lower than the purple line. Sorry, I forgot to say that here on the vertical axis, I actually show this Bayesian mean square error. So our cost function is on the vertical axis. It's also divided by the prior width, such that this quantity vertical shows us how much do we reduce the prior how much do we improve our prior knowledge. So the smaller this value is, the more we gain per one measurement. And now if we continue and increase number of layers for encoder and decoder, we see that very quickly we actually converge to this dashed black line, which shows the optimal result for the optimal quantum interferometer. So one cannot go in this shaded region with any quantum device. And so if we kind of zoom in, we can see that this 2.5 is so close to the dashed line for these 64 atoms that it's hard to distinguish it. And the main goal, the main message is that we can achieve it, we can approximate this optimal quantum interferometer with very few layers of the entangler and decoder. So about the interpretation of the results, what actually did we do? Because we just did the optimization, we found some numbers for the variational, for the twisting and the rotation angles, but what actually happened there? So we can, to understand it, we can plot the Wigner function of the spin state and the measurement operator. So here I show it for this 1,0 interferometer, which is a standard spin squeezed state interferometer with JY measurement. So this gray region is the Wigner function of this state. You can see that it is squeezed compared to the one I showed you previously for the uncorrelated state. And this blue and red colored sphere shows the Wigner function of the measurement operator. So in this case, it's JY measurement. And so how one should read it? One should read it in the following way. So these different color bands for the measurement operator basically shows corresponds to different measurement outcomes. And overlap of the state with these different bands corresponds to the probability of getting this measurement outcome. So if we cross many of these bands, we will get a wide distribution for the measurement. And so here you see this Bloch sphere from the top, and you see that if our state is not rotated, it has a nice narrow distribution around 0. If you rotate it by pi over 3, the state is shifted, it's also narrow and shifted. And if we sort of over-rotate it, here I rotate it in a different direction by 2 pi over 3, we see that it's actually, this orange state looks very much like this blue one with pi over 3 rotation. It means that we actually cannot distinguish them. So here up to this symmetry, if you would rotate it into the right direction, then they would be on top of each other and we couldn't distinguish it. It means that this interferometer has a finite dynamic range, and you can only distinguish phases between minus pi over 2 and pi over 2. Otherwise, you get this phase slip or over rotation. So, and what happens with the optimal interferometer? So you can see that the optimal state is much stronger squeezed now, and the measurement, this optimal measurement operator, looks also quite different from this JY measurement. It's sort of, it's a deformed JY measurement, such that now this color bands of the measurement operator is aligned with the meridians, and therefore the state is kind of fits very well with this measurement operator and overlaps only with 1 or 2 bands at most in a very wide range of values. You can see that now this width of the distribution is more narrow than here, because the state is more squeezed, and most importantly, this rotation by -π/3 is now very different from the rotation by π/3, because it just has you can easily distinguish it. So there is no this phase slip happening here. In fact, the dynamic range of this optimal interferometer is almost from -π to π. And what happens if we look at the optimal at this optimized interferometer with with one encoding layer and 3 decoding layer? We see that it's very similar, looks very similar to the optimal interferometer. The only difference is that now this prepared state is it's not a usual squeeze state, it's a twisted squeeze state, and the measurement operator is twisted accordingly. So in the end, it doesn't matter. So the measurement fits to the prepared state. Why is it twisted? Well, it's because we have used a restricted set of operators, and algorithm decided that that's the best way to do. And you can see that on this probability distribution for the measurement outcome, that it's also very narrow, and most importantly, this -π/3 rotation is distinguishable from π/3 rotation. And now let me tell you very briefly that we actually took this results of the optimization, and we gave it to our colleagues in the experimental lab, and they very quickly, they actually saw that that's exactly what happens. So these are the very new and fancy quantum simulator with ion quantum simulator or quantum computer. It's still in development, but it works very well for 16 ions as a sensor of the phase. You can see that they try different variational circuits here from 0, 0 to 1, 2. And you see with this 1, 2 and 0, 2 circuits, this expectation value of the measurement outcome kind of gets much wider linear range. And what's most importantly, this error of the estimator becomes wide and goes deeper than for coherent spin state. So the dashed lines here is the theory, and dots are the experimental data. So it fits very well. And if we convert it now back to this conditional posterior distribution, so we see that the results are much lower than the squeeze state interferometer or coherent spin state interferometer. So it achieves the best possible. It's actually quite close to the global optimum, and we are actually going to improve it by performing now the feedback loop optimization on the device. So at the moment we did the optimization on the computer. We just kind of found the optimal parameters and gave it to experimentalists. They implemented it, but there are some errors. So they don't know exactly what are the angles of rotations and twisting angles. And what we can do now is to actually run the same optimization procedure, similar one, on the device itself, and then we will include these unknown small deviations, and we can improve the result even further. Let me tell you one thing about this finite range interaction. So previously I considered this global range interaction, like one-axis twisting, but there are systems like Rydberg atoms which do not have this interaction. The natural interaction there is finite range, and actually, we checked, we just tried it out, and it works almost as good as the global interaction. So here we can see that with different number of layers, we can also approach the global optimal. This is only for 16 atoms. calculation, but actually that's not the bug, it's a feature. The problem, or not problem, the interesting thing is that this sort of interaction, this many-body interaction with finite range interactions, we cannot calculate for large systems. It's unsolvable classically, and therefore, in order to go to larger number of atoms to build these quantum sensors made of hundreds of atoms, which are already available for the simulators, we have to do it on the device itself. And that would be one form of the quantum advantage. So this cannot be done classically on the computer, but it can be done by a variational protocol on the device itself. Okay, now let me briefly go back to the clock story. So I showed you how we can build an optimal or almost optimal interferometer for phase measurement. And now we can apply this phase measurement to stabilize the laser or building the clock. And here, the simplified theoretical model of the clock from the theoretician point of view is the following. We want to measure this phase difference between which occurred during the evolution due to the difference in frequency of the laser and the stable frequency of the atoms. And we first assumed that at the 0 time, there was a delta-like distribution for the phase. And then after some time t, the Ramsey times, this phase diffuses, and we perform the measurement of this phase in the optimal way as I described just on the previous slides. And then the how this phase diffusion happens depends on the properties of the laser. So there are different types of noises in the laser. There are so-called just shot noise or random walks. There is this pink noise or flicker noise, and they are characterized by different properties of their spectrum. And in the end, so one of them diffuse the phase stronger or weaker, but the point is that the phase distribution stays approximately Gaussian, and that's what we can use. So as we change the Ramsey time t, it just changes the width of the Gaussian distribution. So we can plug it into our optimizer and optimize the clock this way. So what does it mean to optimize the clock? Actually, so clock is characterized by the Allen deviation, or which measures clock stability, or maybe more precisely clock instability. So it's a ratio of the fluctuation of the frequency to the frequency. So that's called sigma. And if we plot it, then one can write it in this way. So that's the atomic frequency, and tau is the whole interrogation time. So we do many rounds of averaging, and there is a prefactor sigma, this small sigma, that's a dimensionless prefactor, and that's what I plot here. So the smaller it is, the better the clock stability. And so here there are several interesting limits. So first of all, the purple one again is the classical clock made with coherent spin states. And on the x-axis we have this Ramsey interrogation time, which is different one. So there is an optimal interrogation time here, for example, for the classical clock. If we go to a smaller value, then we are now limited by the standard quantum limit, which is 1/√n. Another interesting state for the clock or for interferometry is the so-called JZ state, where it's a superposition of all spins up and all spins down. And it's for the smallest value, it's limited by the Heisenberg limit. It goes like 1/n. It's a well-known limit. A bit less well-known limit is a so-called pi-corrected Heisenberg limit, is green dashed line. It just last year there was a paper about it where they showed that in general it should hold. And actually we can see here that our clocks are basically limited by exactly this pi-corrected Heisenberg limit, because that's where we come in. And dashed line is the optimal quantum clock, which exploits this optimal quantum interferometer. And now if we put in here this small depth quantum circuits, we see that again, very quickly, we approach the optimal quantum clock performance. Red 113 already is as close as it gets. But all these results are basically the results of this simple analytical or semi-analytical understanding with Gaussian noise. But does it actually work in the clock? Because the clock is a much more complicated device. And what we did is our colleagues from Hanover, Clemens Hammer and Marius Schulte, they performed a numerical simulation of the clock, which essentially run some sort of digital copy of the clock for a long time, and they look at this clock stability, so this sigma y, and in the long time, in the long running time, they extract this sigma prefactor, these dashed lines, and if you put it on these curves, they see a perfect agreement. So especially like here, you can see that the clock, it doesn't continue further, because the clock becomes just unstable. So it's not actually, the clock is not supposed to go here. And you can see that to almost close to the global minimum, you can still follow and see that this very precise clock simulation agrees with our results. And with this, I would like to come to the conclusion of my talk, where I showed you that using the variational quantum algorithms, we can actually sort of unify the field of quantum simulators and quantum sensors to build a programmable quantum sensor, which has a potential to achieve optimal result, which allows us to build almost optimal interferometer. And most importantly is that the low depth variational quantum circuits can do it. And it's it's reasonably simple, such that experiment can be done well just on a month length scale. It was done with Ein quantum simulator, but as a further kind of improvement of this approach, of course, lies in this on-device optimization, which in the end can allow us to build clocks made of large number of atoms, and thus achieve and improve beyond what is available at the moment. This is not only concerns only clocks, it's also magnetometers, which is essentially very similar thing, where you measure phase due to shifts of the frequency because of the magnetic fields, or other quantum sensors. And thank you for your attention. This is our theoretical group. Rafael Kobrugge, our physician, mainly work on this paper. Rick is doing the optimization. Peter Zoller is our team leader. And this is our colleagues from Hanover, and the great experimental team of the Innsbruck University is in here. So yeah, the paper is available on arXiv since a few weeks ago. So thank you very much.
Thank you for this amazing presentation, Mr. Vasilyev. So if you have time, we have a few questions from our listeners.
Sure.
So the first one is, someone asked that what does Wigner function of an operator means? Does it mean the expected value of operators?
No, it well, you can actually build Wigner function of you can think of Wigner. Okay, if you decompose the operator into its eigenstates, then you can plot the Wigner function of each eigenstate and plot them all together on the same Bloch sphere with corresponding eigenweights, and it will give you this picture. But in the end, the Wigner function of state and operators, they are the same, because when you plot the Wigner function of a state, you plot the Wigner function of its density matrix, which is an operator. So Wigner function is not restricted to a state. It's applicable to an operator. And as I said, in this case, so you can read it as so different color bands just corresponds to different measurement outcomes.
Thank you. So another question would be, someone asked that would using non-Hermitian Hamiltonians give us an advantage on calculations for quantum computing and on this research?
Sorry, could you repeat it from the beginning?
Would using non-Hermitian Hamiltonians give us an advantage on calculations in QT or in this research?
Non-Hermitian Hamiltonians. So you're talking about dissipation. I'm not sure it will give immediately an advantage. It's certainly a possibility. So at least for the sensors, this encoding stage, it can be a non-unitary evolution. There you have to use the non-Hermitian Hamiltonians, or more precisely the Lindbladians. Well, I'm not sure it will give you an improvement. Maybe sometimes you have to use it because of your restrictions. Because in the whole variational approach, you work with what is available. If your gates are somehow dissipative, well, you can use it and find the best way to exploit them to minimize the cost function and achieve the result.
Thank you. So another question is from Nelkant Kundul. They ask, why do you assume a Gaussian prior instead of some circular distribution like Reb Gaussian or von Mises prior for phase parameter?
Well, the main motivation for considering the Gaussian prior is because clocks, which we have on the back of our mind when we consider it, because clocks, they naturally produce Gaussian random number, this phase. Well, it's not exactly Gaussian, but it's with very high precision, it is Gaussian. But in the end, it doesn't matter that much, so you can actually put in there any prior distribution you are interested in. It depends on your measurement task and on your sensor. So you should look at what are you going to measure and with what type of device, and then you will see what is the proper prior distribution. But the whole approach works for any distribution. Just for clocks, it happens to be Gaussian. And well, Gaussians are generally, you can find it everywhere in nature for some reason.
Thank you. So I think this one is also related to your answer. And they ask, why do you prefer Wigner pseudo distribution? Is it because of interferometry applications since Wigner distribution in coordinate space?
Sorry, I didn't get it. Why do I prefer to what? I mean, here the Wigner distribution allows you to kind of visually see the state and the measurement operator and understand why one works better than the other interferometer. I mean, I don't see an alternative to the Wigner function in this case. Oh, maybe Husimi function, but it's sort of the same thing.
Thank you. So the other question is, could the method in this research is applicable on different interferometers like Mach-Zehnder interferometer? Yeah,
it is applicable. So the whole Bayesian approach is applicable to any interferometer, and this particular one is also. It's not restricted to clocks or magnetometry. It works everywhere. It just depends that it certainly depends on the interferometer, and you should kind of look a bit carefully into what do you have there. For example, Michelson interferometer used for gravitational wave detector is a little bit different. But for like technical reasons, there you don't have spin, you don't have this restricted fine dimensional system. There you have light of very high intensity, and you don't see this non-linearity of the spin Bloch sphere. But general approach is, of course, kind of applicable. Well, it's not even invented by us. It's done by other people and used for a long time.
Thank you. So there's also another question They asked that the phase you have shown is for time measurement looks like a dynamical phase, which usually referred as not a real phase. Do you directly detect this or phase or calculate it?
Sorry, about this calculation, what do you mean? It's a dynamical, where is this clock thing? Yeah, it was in the beginning. So I mean this phase. Yes. So could you repeat the question again?
Okay, and I will also send you through the chat for easier
Yes,
access.
let me try to
So
read
the
it.
question is, the phase you have shown is for time measurement looks like a dynamical phase, which usually referred as not a real phase. Do you directly detect this phase or calculate it?
I'm not sure what is real phase and or not real phase. This phase is very much real because it gives rise to shift of your atomic spin, and what you measure is basically the angle of rotation of your atomic spin. So this phase, which is given by the difference, the integrated difference between the laser fluctuating laser frequency and the atomic frequency, is kind of precisely encoded in here. So here you should put this integral in this free evolution, and the evolution of atoms is just rotation. Well, the rotation around z by angle phi, and phi is random. So we just measure this angle of rotation. Is it real phase or not? To me, it's real. But directly, what I measure directly is, of course, the projection of the atomic state on the Jz spin component. So that's, and the distribution of your measurement outcomes look like this. Yeah, in the end, it's a project. It's how many atoms are up or down after the protocol, and then you have to infer what was the phase, real or not.
Thank you. So I'm looking if there's any new questions. It doesn't look like so. So thank you for your presentation today here. I think it was very informative.
Thank you for having me.
Thank you for coming also. And do you have anything else to add?
Sorry?
If you have nothing, do you have anything else to add?
Oh, no, thank you.
Before we
Thank you very
finish?
much for inviting. Yes, I can stop sharing.
Thank you very much for coming. So we will give a small break right now before our next speech, and we will tell you when to come before. And for the next one, the speech will be in 15:30 or in 20 minutes. So see you soon.
quantum circuits, they low.
Welcome back, everyone. So we will be waiting a few minutes for everyone to get in. And before we start and move on to our speaker, there is an announcement that we would like to make to our Turkish attendees. So there, Koç Üniversitesi QSB ekibi tarafından bu konferansta da konuşmalarda da göreceğiniz ve karşımıza çıkan dolaşıklık, uyumsuzluk, kuantum uyumsuzluk gibi kavramları inceleyeceğimiz, bu kavramların çeşitli kuantum teknolojilerinde uygulamalarını içeren bir mini ders serileri hazırladılar ve bunu ders sunumu halinde verecekler. YouTube Commons'larda bununla ilgili linki ve form başvurusunu bulabilirsiniz. Konusu kuantum teknoloji ve kaynak türlerine giriş ve QTalks incelenecek. Güzel bir etkinlik, kaçırmayın derim. Formu YouTube'da paylaşacağız. So, our next speaker is going to be Michal Stechly from Zapata Computing and Quantum Open Software Foundation. He will be giving us a speech on what quantum software engineers do, hands-on examples. And before we start, I would like to introduce you to him. Michal is a quantum software engineer at Zapata Computing and a core team member at Quantum Open Software Foundation. He's working on quantum computing algorithms and interested in optimization, software design, and data visualization. So hello, Mr. Stechly. Welcome, and thanks for attending to our talks.
Hello, thank you for having me. Nice to be here.
So how are you today?
Yeah, I'm fine. I actually liked the unexpected change of schedule, so all good.
Yeah, it had to happen that way because of some minor changes in the program.
Oh, sure.
So, yeah, if you are ready, we would start. You can start. So
Okay.
You can share if you want to.
One moment. I will share it like this. Okay, do you see my screen?
Yes, we can. So I'm leaving the stage for you.
Okay. So one last question. Oh, actually, I'm hearing that someone is getting in. If we can disable it, because like it might be annoying. But one question I have is, oh, please let me know when I'm over time. I'm looking at my timer as well, but just in case, because since the timeline's changed, I don't know, like, don't want to get too much overtime, but I can talk for hours. So,
okay, I will be letting you know via messaging on YouTube.
Okay, I designed the last slide so that I can either go into that and show more examples, or I can wrap up earlier. So I'll probably ask in the end, but just to be on the safe side. Okay. One more thing. Okay, good. Then I think we are good. Cool. Cool. So, welcome everyone. My name is Michal Stechly, and I am quantum software engineer at Zapata Computing. And I would like to tell you today a little bit about the job of quantum software engineer, and specifically to give you an example of what my job looks like on a daily basis. So a little bit about me. So as I said, I work as a quantum software engineer at scientific software team at Zapata Computing. I'm involved, given that Zapata is a startup, I'm involved in many different things. So from product development, a little bit into research, but also sometimes helping with the customer projects. I'm mostly interested in variational quantum algorithms and optimization. And apart from that, in my spare time, I'm running a mentorship program at Quantum Open Source Foundation. I write a blog and recently also a podcast about quantum computing. And in general, I try to help get people on the next level with the quantum computing. Okay. So I wanted to also say something about Zapata and orchestra, just if you don't know. So Zapata is a quantum software startup, and we have offices in Boston and Toronto, but also many people remotely. And specifically, I wanted to tell you what orchestra is, because I might be referring to that throughout the presentation a couple of times, so that you are not lost. So orchestra is a workflow management system for quantum computing that we have created at Zapata. And basically, it allows you to express an algorithm, express the computations you want to run as a workflow that you can then run on a cluster that can connect to different quantum devices. And that's basically it. So if I mention orchestral workflow, this basically means, well, algorithm written in a very specific format that we are running on orchestra. If you want to learn more, there is more on our website. I hope this will be published on YouTube afterwards. And in case someone is watching this on YouTube, I will provide the link to this presentation so that it can be under this video. And other people who are right here, right now, also would be able to refer to that. Okay, so let's get into the topic itself. So what's the role of a quantum software engineer? The way I see that is that quantum software engineers are people who are bridging the gap between science and software, mostly by creating tools for scientists, but also creating tools like from what scientists did, so that other people can use it. So two examples of that. One is a situation where scientists wants to run some algorithm, but they would like to run it on a specific simulator, and we are writing them the integration for that simulator. Well, making sure that the simulator works correctly in your environment, that you have all dependencies installed, and so on, is not really particularly scientific. It's mostly software task. So it makes sense so that software engineers do that and scientists focus on the research. And on the other hand, also someone comes up with an algorithm or a new method, and then we take this algorithm and just make sure it's easy to use for others. So we make sure we are checking there is proper documentation. We make sure all the tests are in place. We make sure it actually covers all the cases that it should. And I'll show you examples of what I exactly mean by that later on. So how this job is different from a job of a researcher or a scientist? Well, it is very different, because mostly it's about writing software. And I talked with many colleagues in various companies that have similar positions. And across the field, it's pretty consistent that 80% of their time is spent on writing software, and maybe 20%, maybe less, on doing some science and research. It's not the regular software engineering job, though, for many reasons. One of that is that I think the domain knowledge is much more important here than it is for people who are writing web applications for, I don't know, banks or for e-commerce or stuff like this. It's quite different. We also are working very closely with scientists, which is really nice, but also, it's kind of specific type of cooperation. We need to have very high resilience in this job, because the field is very new, and there are, it's still evolving. So often you write some code and it turns out not a long time after that actually it's no longer important, like no longer useful, because either our understanding of some concept was wrong and we just got the science wrong, or that someone released some new results recently and basically now we have better methods. So often it's about 2 steps ahead, 2 steps forward, 1 step back, just because the field is changing so quickly. It also involves some DevOps work, like setting continuous integration, pipelines. Like recently, I've been writing GitHub actions for our repositories so that we have automatic style checks and much more. One thing that I wanted to emphasize is that it is a team effort, and the amount of domain knowledge that one's need is really big. So here is our team. You can see who has like degree in what, and also like what's our specialty and background. And this slide here is to show a couple of points. So first is that there is not a single person that knows all of that, and we rely on each other. The second is that we have complementary skill set, and we can, by working together, we can really leverage one's knowledge. So for example, Konrad is a very good Python programmer, and whenever we have some problems with how to do something in a really elegant or efficient way in Python, then like we ask Konrad. But for example, given that Max has a background in material science and chemistry, then whenever we need to write some code in that domain, well, the Max is either the person that does that, or actually just the person that helps us understand the domain better. And also I wanted to point out that even though this domain expertise is super important, we have on our team Alex, who actually has no background in, or at least not official background in physics or quantum computing, and he's learning this on the fly, but his expertise in machine learning and also just all sorts of software engineering makes him really valuable person in our team. And I have a podcast called Noisy Intermediate Scale Podcast, and the first episode was exactly about this topic. So what quantum software engineers do. I talked more about the challenges that we face, some typical types of tasks, what are job requirements, and much more. So if you're interested, you can find it online and listen to that. But today I didn't want to just say all the things that I already said there. I wanted to give you an actual example of what I was working on recently. So I will show you the code that I've written. I will walk you through the process of writing this code so that you can get better understanding of the whole process and of the actual, what this job entails and how does it look like. Okay, I'll just have a sip. Okay, so today I would like to tell you about our implementation of warm start QAOA ansatz. And I've chosen this particular project for a couple of reasons. So first, all the code that we have written for that is open source. So I'll be showing it throughout the presentation. You can also find it on GitHub. And this is something I worked on recently, so I remember pretty well how it looked like. I don't like to talk publicly about projects I did half a year or a year ago. It's a little bit more on the scientific side of what we do rather than regular software engineering. So I thought it will be more interesting for you. And also we did this in the cooperation with the research team, so I can also show you a little bit how such cooperation looks like. So how we quantum software engineers work with the research team. And here we have the paper, and I hope you see not only my presentation, but now right now my browser as well. So there was this paper, warm starting quantum optimization, and by this fine authors here. And you will see that throughout the presentation, I will be showing some snippets of text or equations from this paper. So if anyone is interested, this is where they can learn more about the algorithm itself. And before we actually start, I wanted to warn you that this talk is about the software and not the science. So if you would like to get a deep understanding of the algorithm itself, the methods, well, that's not here. Just go and read the paper. Here, I will show you the process of changing the paper into the code, but without actually getting very deep into the scientific and algorithmic nuances, only as much as it's necessary to explain the concept. Okay. So it all started roughly in December 2020. And as you can see, we have a researcher here in the left corner who has some ideas. And you can see quantum software engineer just squashing some bugs in the bottom right corner. And basically, at some point in December, guys from the research team came to us and said, you know, we would like to use warm starting QAOA for one of our projects, and whether we could help them with the implementation. And like, yeah, sure, of course. You know, what's the timeline here? And they said, well, we want to have it ready around the beginning of the April. So we said, well, it gives us roughly 4 months to work on that. So yeah, that's a very reasonable request. And the first thing here that I wanted to highlight is, at least at Zapata, it usually works this way, that the scientists know in advance what research they want to do. And if they come to us and ask us to help with some implementation, they actually do that ahead of time, so we can all prepare better and schedule, you know, our job, our work in advance. And that's pretty important because, as it turns out, often these things take longer than one expects, as we will see. So yeah, just send me paper and we'll talk about it. So how it looked like. In December, we got a rough plan of all that we needed for this particular project. And that was not only the warm start part that I'm talking about. There were like some other features that they wanted to use in the research, and that required a lot of different things to implement. So we started implementing these features one at a time. And basically, we had a huge list, not that huge, but like a list of all the things that they wanted to have in our software, and we're just every week taking one of them or not, and just going through that list so that we will be ready with all the parts for the beginning of the April. And also we had a weekly meetings to stay in sync about the software and about the needs of the research team. So basically, we are meeting every Wednesday or Thursday for half an hour to just talk. Okay, so research team is doing research on this and that, and they actually something changed and they need this part earlier, or they actually this other feature is no longer important because something changed and they realized it's actually there are different ways to solve this problem. And I'm giving them updates on like where we are on the software side of the things. So the first phase of that was planning, And actually, that wasn't very complicated in this particular case. And for the particular feature of warm starting QAOA, well, I just needed to read the paper, talk with the team to make sure what's the scope of the project and whether we have to implement the whole paper or just like part of that, and then just code it. So, it's not particularly complicated plan, but it was worth just, going through the steps to make sure everything is okay. Okay, so let's talk, what is the substance of this project? So what the warm starting QAOA is even all about. So before we start, actually what the QAOA itself is. So if some of you don't know, the QAOA is a quantum algorithm which allows us to find the ground state, the solution to so-called Ising problems. And as it turns out, we can express many combinatorial optimization problems like traveling salesman or graph coverage problem as Ising Hamiltonians, as Ising problems. But since Ising problems are equivalent to quadratic unconstrained binary optimization problems, so QBO, we can translate these problems to QBO as well. There are like basically two representations of a similar thing, and sometimes we prefer to use QBO, or sometimes we prefer to use Isings. And one property that both these problems have is that they are both binary problems. So the output, the solution to the problem is just like 0 and 1, or in the case of Ising, it's actually -1 and 1, but that boils down to the same thing. And well, the problem of the integer problems is that they are often harder to solve than continuous problems. So if we have this, little function on the right, you can see that if we just like draw the whole curve, it has this shape, right? And we can use some nice methods, well known, like gradient descent, to just start from any point and just get to the bottom of that and see that the minimum value is at x equal 0.6. But if we say that we want to solve this problem not in the realm of the real numbers, but in the realm of integers, well, it's only defined from the integers on 0 and 1. And this is a toy example, but it's not that obvious how to, maybe not that obvious. There are like very different methods for solving this type of problems rather than continuous variables problems. So one thing that people in the traditional, like classical optimization world figured out is, hey, maybe we can relax this integer problem into continuous variable problem. So instead of saying, the only viable solutions are those given by integers, we say, actually, we can use any real numbers we want, because this will make this problem easier to solve. And then we'll use the solution we obtained from the relaxed problem, so this 0.6, to somehow help us get the better solution for the integer problem. And indeed, if we just go with the very, very simple and naive method of just rounding the continuous solution, so if we take 0.6 and round it, we will get 1, which is the correct minimum in the domain of integers. Well, this is very contrived and simple example, but it's one idea of how to deal with this type of problems. And the main idea of the paper is, like people used it in the classical optimization for quite some time. So why don't we just use it in QAOA and see how it works? So that's basically it. So when it comes to planning the, after reading the paper and talking with the team, we decided that what we need to do is A, implement the warm starting QAOA ansatz. And if you don't know what ansatz is, I will explain that in a moment. Then B, write code which will solve the continuous relaxation of QBO. So as I said, continuous relaxation means that we take solve the problem not in the integers but in continuous variables, so like real numbers. And then we needed to write an orchestral workflow to run this code. Now I won't be talking about the last part because it will require too much of actually explaining how orchestral works. So we'll focus on the first 2 points. Okay, so first thing, ansatz. If we go to the paper, we'll see that one version of the ansatz looks like this. And, well, it doesn't seem particularly complicated. It starts with some initial state, so rotation y of like theta, and we have theta 1 to theta n, so basically a vector of thetas. And those thetas are some angles that are calculated based on the solution of the relaxed problem. Okay, so we first solve the problem in a continuous variable way. This gives us some numbers, and then we translate these numbers to thetas. So that's what's it. And then we have standard QAOA construction, which is some subcircuit based on the cost Hamiltonian, defining the problem, parameterized by the angle gamma, and another part called the mixer Hamiltonian, like mixer part, associated with the angle beta, right? And then we just repeat this whole thing p times. So p is number of layers. So one could think, well, that looks like super easy implementation, right? Because we just need to write something that looks like this, right? So we create a circuit, and we start with the layer of Ry gates, and then we add, exponentiated cost operator, and then a layer of Ry, Rz, and Ry. And actually, I just realized that I totally messed the gates here, so please don't worry about it. It should be Ry, Rz, and Ry, and the parameters are also wrong. But that's basically how one would approach solving this particular problem. But actually, it's not that easy, and I'll show you why. If you were to just write your own small project and you didn't care whether other would have hard time or easy time using that, then you could just write something like this and that would be good. But actually, with Orchestra, we have defined some structures some objects that allow us to get much more of that. So implementing such ansatz, requires a little bit more effort, but actually it pays off very well in the future. So what I'm talking about is something I call ansatz interface. And if you can see my browser, please kind of react or let me know in the chat or something, because this is pretty crucial.
Yes, we can see it.
Awesome, thank you. So here we have something called like a class, an abstract class, ansatz. And this class defines an interface of how we want all our implementations of the ansatzes to look like. So you can see it has like some init, It has a couple of functions, a couple of methods, right? And maybe the first thing is, okay, why would we do that? Why would we create a base class called ansatz instead of just, everyone writing their own ansatz classes? So the reason is that, let's say we want to compare two ansatzes. So we want to give the same problem and basically give the same inputs, use the same simulator, use the same optimizer and everything, and just compare how regular standard QAOA ansatz compares with this warm start QAOA ansatz. So the problem is that if we implement it in a way where everyone can implement their ansatzes as they want, they might implement them in a way that they have different interfaces. So the functions have different signatures, and they take different objects as input, and so on and so on. And they also return values in a different format. So in order to unify this, we create interfaces like this. So for example, let's take a look at the parameterized circuit method here. So this method, well, when we just call it on the ansatz object, it returns a circuit. And what it does is that it allows us to have a mechanism to not calculate the circuit for the ansatz every single time. So some ansatzes require some extra computation in order to calculate how the circuit looks like. And so this might be pretty, computation heavy and time intensive. Not extremely, but still, you might want to save that time. So what we do is that we check if the private field of this class parameterized circuit is none. Then we create such parameterized circuit with the generate circuit method. However, if it's not none, then we just return the parameterized circuit that has been already created, right? And also, as you can see here, this is for creating parameterized circuit. So the circuit that doesn't have the actual numbers inside. So the beta and gamma angles are just symbolic parameters. So if it doesn't support symbolic parameters, then it throws some exception. And the important thing here is also that what happens if the number of layers or the cost handle, something changes, maybe just something changes in our parameter, number of layers, and well, then we cannot use this parameterized circuit that we already had calculated, right? Because, well, it changed in the meantime. So now if we just change the number of layers, we need to recalculate the circuit. And the nice thing is that the way we coded it is that this number of layers is defined as ansatz property. And if we ever change the number of layers, then it sets the parameterized circuit to none. This code is in one of the helpers, so it's not here. But then we know that we need to recalculate the circuit. And this all is in the base class, which is an abstract class. So every class that inherits after this will actually have this mechanism built in. So it's super convenient because you don't need to worry about it and write this logic every single time. Okay, so, and also you always know that if you call a get executable circuit method on your ansatz, you will get a particular output, and it's not that you have different methods called get circuit, get executable circuit, get circuit with parameters, and so on. So it's nicely unified. And so that's one benefit. The other benefit is that we have tests for all that. So we have a base class with tests, and actually we can check all the things, some of the things that I talked about. So for example, we have this test set number of layers invalidates parameterized circuit. So we check whether if we set the new number of layers being 100, whether this private field parameterized circuit is actually none. And we can inherit these tests for the children classes as well. And this way, we know that all the ansatses that we'll implement later actually pass this basic test here that we defined. Okay, so just as an example, this is a standard QAOA, so like Farhi, the one defined in the original Farhi's paper. And it has cost Hamiltonian, it has mixer Hamiltonian, and basically it generates a circuit based on like how it was defined in the paper. And as you can see, this implementation itself is not that big. It's roughly 80 lines or so, because a lot of the logic that we had is in the base class, right? So we didn't have to write the parameterized circuit method because it's already implemented in the base class, but we just did have to implement the generate circuit method. Okay, so now let's take a look at the actual warm start ansatz that is what we care mostly about here. So you can see that we have cost Hamiltonian and we have thetas. In the Farhi ansatz, we had mixer Hamiltonian defined, so we could pass the mixer Hamiltonian. But here, well, the mixer Hamiltonian is always the same. It's defined by thetas, so we just use thetas. And here we have the code for generating the circuit. And as you can see, well, it's slightly, this is basically the snippet that I showed you here. It's just a little bit more involved because, well, we check whether the params are none. We do some, bookkeeping, and the syntax is slightly different, but that's basically the same thing. And of course, once we got that, well, we also have to write tests for this, right? So here we also have tests. As you can see, they inherit after the base class, and well, we just test whether whether it works. But this is like if you have written code without writing tests, you have not written the code because you don't know whether it works. So this is how the tests look like. And when it comes to implementing the ansatz, well, that's basically it. Like that's the whole thing that needed to be done. So, oh, there was like one little one more thing. So we also need to have a method which somehow converts the C, which is like the solution to the continuous relaxation, into those thetas. And well, it just looks like this. And this is from the paper. So they said, okay, we decided to do the conversion this way for the following reasons. And I just took this and implemented this as a bunch of if-else statements. That's it. I mean, that was pretty straightforward thing to do. Okay, so now we get into the third phase. So first was planning, second was implementing the ansatz, and third is actually solving the relaxed QBO. So the starting point for this part of the project was the code I got from my colleague Guoming that he used for this particular problem. And this code was using a CVXOpt package. And while the code was doing the job it was supposed to do and it was working properly, it had a couple of issues that we had to solve before incorporating that in our code base. So first was that it used a custom QBO class, and actually in our framework we use the QBO class defined in the D-Waves library Diamond. So there was a little bit of refactoring to make sure that actually his code uses the class that we are using in the rest of our code. Second thing was that he was using some custom CVX-opt data structure, which also wasn't a particularly good idea for the production development, for the production code. And also there were, some assumptions hidden in the code that we wanted to state explicitly. And for example, check whether given parameters have values from given range or different things like this. Well, it turned out that this part was harder than I expected. So the first challenge was to decide whether to use what package for convex optimization to use. So there are two packages in Python. I would say like two most popular packages for this. One is called CVX-opt, so convex optimization, and the other is CVX-pi. And Guoming started from CVX-opt, and later he discovered this CVX-pi, and he was wondering which one we want to use. And we could use either of them, but we had to choose one of them. So how do you choose what package to use? So here I will just walk you through my method of doing that. So I go to GitHub and I look how popular the package is. So we see that CVX-opt is slightly less popular. I mean, maybe not slightly, but like less popular than CVX-pi, looking at the number of stars and forks. But that's only one part of the story, because maybe one of these packages is just 5 years old and the other is 1 year old. So this doesn't give us enough information. So the next thing I usually look at is the releases. So how often the new versions of this package are released, and also how actively it's being developed. So as you can see, the CVX-opt, the last release was in February, and I was making the screenshots like 2 or 3 days ago. So this one was still in March. So it looks like this is the CVX-pi is being released more often, and also it has many more releases. It also has many more commits, and actually, as you can see, the last commit on the CVX-opt was the same time as the last release, while CVX-pi is being maintained regularly. In addition to that, CVX-pi had more examples in the documentation and basically just cleaner docs. So I decided to go with CVX-pi. And this is pretty important because I was both in situations where I've chosen a package without too much thinking and looking, that there was a good package that seems as a very reasonable solution, but I haven't noticed that it's no longer maintained. So when I hit a problem or found a bug, there was no one there to help me, and there was no one to answer my questions. While I also been in the situation where the package is very well maintained, and basically, I ask a question and I get response, and that works very well and makes just development so much easier. So the next issue with this part of the code was the representation. Not even representation. So you'll see. So we defined QUBO as the following problem. X is the binary vector of that represents our solution, and sigma is a matrix, and mu is a vector. So we basically want to minimize this number here. And this is the definition of QUBO in the binary variables. However, if you want to relax it, there are different ways to allow for the relaxation. So one of them is that if the sigma matrix is positive semi-definite, we can just say that we minimize this part here. So x sigma x. And as you might see, we don't include the mu term, and don't worry about it. We'll talk about it in a moment. Right? And basically, we have a problem like this. X is now not a vector of either zeros or ones, but the vector of the values from 0 to 1. And we can use this with the classical solve this problem with the classical optimizer. That's fine. But also there is another way to get the solution, which is called semi-definite programming. And it does some magic. I don't fully understand how it works, to be honest. But basically, there are two methods presented in the paper how to get the continuous relaxation. And the problem is that, well, the one is called semi-definite programming, and the other checks whether the matrix you have is positive semi-definite. And well, these terms are dangerously kind of similar to one another. And when I was reading that, and when I was talking with Guoming about it, I got totally confused. And I was mixing the SDP with positive semi-definite. So you can abbreviate that to PSD, but actually in my head, for some reason, I was calling it semi-positive definite, so SPD. So in my head, this was SPD and this was SDP, and I just got confused. And I was reading this, I was talking to Guoming, I was reading the paper, and I couldn't understand what's happening because everything that he said was making no sense to me after I read the paper. And I didn't know whether we want to implement the SDP case or SPD case or something else. And finally, in one of the conversations we had, he pointed to me out that actually this is probably the thing that I'm confused about. And then I realized that, oh, indeed, so like the positive semi-definite thing and the semi-definite programming are two things. And right now, when I look at this, to be honest, like it's pretty obvious, and they are not even using any abbreviation here, and like it's positive semi-definite, so there isn't even place for the abbreviation like SPD that I had in my mind. So I just got confused and I wasted a good couple of hours just trying to understand what's happening here. And I'm talking about this just to show you that these kind of things can often just be confusing, and you might not have the full understanding of what you are doing. And it's important to have someone that actually understands this problem really well, if you are not such person. And if you don't have anyone else that understands it better than you, then you really need to dive very deeply into this. So another problem that we had was the fact that in one representation you have this mu vector here, and in another you don't have. And well, in the paper they mentioned that you can incorporate this mu into the sigma, so you will have like a modified sigma, but it wasn't obvious how to do this, whether we need to do this, and how to account for that. And also the representation that they have in the diamond package actually kind of already have this incorporated into the matrix. So it took some time to kind of understand how do we want to deal with that. And actually, this wasn't a big problem, but this was, I had two problems. So this like SDP confusion, and also this how to tackle this me term confusion. And two of them, they just, well, made me waste significant amount of time trying to figure out what's going on. But finally, we managed to do that. And we written the code. And this is how the code looks like. So if you take a look at this, this is actually not that much of the code. So this is for the case of semi-positive. Oh, positive semi-definite. So you can see that like here is SPD matrix. It's actually wrong abbreviation. I should fix that. It should be semi-positive definite, and it should be positive semi-definite. So you see like the kind of traces of my confusion even here in the code. Yeah, I notice it right now, so I will fix that. But you see that this is actually pretty simple code, because this is actually a pretty simple problem. There is a little bit of bookkeeping to translate the problem into the format that the CP, which is CVX-Pi, how it works. And also we had another version of this function where if the matrix is not definite semi-positive, no, positive semi-definite, yeah, then we just use a classical optimizer with constraints and we solve this. So, that's the code. There are also associated tests with that, of course. And there are a couple of issues with the code that I've written. So one was that there were some, I thought that it's all done, but actually it wasn't, because for one, there was like numerical errors. So it turns out that if you use the optimizer, a regular optimizer with constraints to do this, you can get values like 1.0002 or -0, basically. And this is bad because in order to translate those solutions to thetas, you are using arc sinus function, and well, it doesn't like values outside of like 0, 1. So it was throwing some errors. So, well, it was a bug. I added a rounding here to make sure that if we have some numerical imprecisions like this, then we'll get our value rounded. But at the same time, if actually it's not due to numerical imprecisions, but something that's more significant than 8 decimals, then it will just return whatever we wanted. Well, there were some issues with running it on orchestra, and I had to debug that. And also, it turned out that the way the problem is defined, this part of the code, which solves the problem for the positive semi-definite matrix, actually always returns a vector of zeros, no matter what's the input, just from definition. So we just realized that actually we didn't even have to wonder whether to use CVX-Pi or CVX-Opt, because it will, no matter what you use, you will always get a vector of zeros. We decided to leave it the way we have already written that, because it's not very computationally intensive anyway, and might be useful in future if we decide to modify it. But it was quite a surprising realization at some point. So since I don't have too much time left, lessons learned. So, well, implementing algorithms is hard, and I thought this will take me about 2 or 3 days, because I just looked into the paper, I looked at the ansatz. The ansatz looked easy, and I thought, yeah, that's easy task. But it actually took me more like 7-8 days of work, so roughly 2 weeks. You can, well, I also estimated, like, have not estimated properly the amount of work, because I had convex optimization when on one of my university courses, and I basically knew more or less how it works. But actually that was a good couple of years ago, and as it turned out, I didn't really remember very well how to deal with that. So I needed some refresher. And it's a good lesson for me that, well, the stuff that looks familiar because you had that knowledge a couple of years ago doesn't mean that you still have this knowledge. And maybe it's more complicated than it looks. And also this, as I mentioned, this shows how important it is to work closely with someone who actually understands the domain of the problem, understand the science of the problem very well. Because, well, this gave me the comfort that I didn't have to read the paper in very detailed way, and I didn't need to actually understand all the details of what's happening there, because I could always ask Guoming. On the other hand, if I was to implement it by myself, yeah, I would definitely spend much more time, learning about the problem and understanding it much better. So, well, that's it. I guess that's the last slide. So just to give you a little bit more idea of what are some other things that I've been recently working on, which are maybe not necessarily as algorithms oriented. So one thing was translating between weighted Pauli operator in Qiskit and Qubit operator objects in OpenFermion. With the link to the code, there was one task where with my friend Alex, we were adding different graph problems than just MaxCut to our library. And like he was mostly coding, I was just helping a little bit. Then actually in order to write the code that you've seen, I had to refactor the whole ansatz, like the test for the ansatz base class, because the tests were written in unit tests and we are now using PyTest. So I just had to go and like fix all the tests. There were some, bugs in the conventions of the QO that was, well, that's, I can talk about what happened here for another hour, I guess. That was pretty confusing as well. And apart from that, a lot of other things like simplified typing, a lot of design discussions, decisions about how do we want to release our software, how we want to perform serialization and other stuff. I've added GitHub actions for automatic style checking and things like this. There is a lot of writing internal documentation and guidelines recently, and also like just improving some internal processes. So that just to give you, better sense of what I've been working on in the last month or 2 months, except for this warm starting QAOA. And also I wanted to once again emphasize that it's all team effort, and I couldn't do like any single of, well, maybe not any single, but like most of this tasks here involves more than one person, more than me. And I, for example, with this debugging QBO conventions, I was getting a lot of help from Conrad, who has much more experience with QBO and Ising problems. Here I was doing this with Alex. And for example, with this weighted Pauli operator, I was discussing how we want to handle that with both Max and William on our team, because Max knows, he knows our code base better and the OpenFermion package better, while William has more knowledge about the Qiskit. So, I asked them. So, it's all team effort. And I don't think, and I think it's super hard, especially in quantum computing, to be a lone kind of developer, just because there are so many things and the science of all that is so vast. Okay, so that's it. And I wanted to ask if you have any questions.
So thank you. Yeah, so I'm reverse again, but there's nothing I can do right now. So thank you for your presentation, and we have some questions that we would like to ask from our attendees. So the first one is that, which platform do you work on? Qiskit, Microsoft Azure, or something other, and why do you prefer that one?
Sure. Oh, so I will answer just like I forgot. If anyone is, you just forgot to say, like, you can find me here. You can find me on Twitter as well. I'm sometimes throwing some, content interesting. If you like this, then I'm also publishing some interesting content there. So you can also find my blog and podcast. through my Twitter. So just wanted to make sure that if anyone is looking for more information about it, they can find it there. Answering the question, well, we are actually, regarding that, we are platform agnostic. So we have our own circuit class, which translates between Pikewell, Qiskit, and Circ. And the way we designed Orchestra is that you can use, you can write your code in any of these languages and just translate it to another one, or translate it to like the format that we are using, and that's it. So it's like doesn't matter really what platform you are using. I personally prefer to use Pikewell for like my personal projects or like for small prototypes, but that's mostly because when I started doing quantum computing about 2 or 3 years ago, Pikewell was much more user friendly, and I just like started from Pikewell, and I know it best. But I think that's like just my personal preference, and there's like I don't have a very strong reason why I use this like Pikewell in favor of Qiskit or Circ, rather than just like me being familiar with that.
Okay, so we have some research-related questions that I want to ask first. So on the specific topic that you talked on, so how do you design the mixer Hamiltonian in the case of VSQAOA?
Okay, so one moment. Okay, so basically, it is designed like it's described here how you design the mixer Hamiltonian, and here is the equation. I don't have really anything more to add here. So here's the equation, and here is the how this equation translates to a circuit. And I guess that's it. I mean, like you can read more about this in the paper, why they did it in this particular way. But yeah.
Thank you. So another one related. So can we consider QAOA as a variant of quantum alternating operator and sus algorithm?
Can we? Could you repeat?
Can we consider VSQAOA as a variant of quantum alternating operator and sus algorithm? I'm going to send you in the chat also.
I know what you're referring to. Thinking. I don't remember the definitions that Stuart used in his kind of paper where he described this. I think so, in principle, because the alternating. Oh, I always forget the name, but like I will refer to it as like Hatfield's QAOA. So like Hatfield's QAOA is, as far as I remember, a generalization of the regular QAOA, and it just gives you more freedom over what you do with the mixer Hamiltonian and the initial state. And well, this is what we see here, like more freedom around it. But I'm not sure for the one reason, which is that actually the most of the Hatfield's paper about most of the examples that he gave were the examples where he was starting from a feasible solution to a problem and then designing the mixing Hamiltonian in such way that it allows you only to produce other viable states, right? So if this viable solution to a problem is a state where you have only zeros and just one, then the mixer Hamiltonian would transform the state that looks like this into another state that has one but in different position. While in here, we actually, it's more complicated because you have those states that are like rotated by Ry. And you can get an arbitrary, I mean, not any state, but like a lot of different states that are not feasible solutions to the problem because they are superpositions. So because of the rotation. So actually, I'm not 100% sure whether you can treat this as alternating layers or like Stewart's, like Hatfield's QAOA. I think so, but I would need to check the paper and the definitions to say that with kind of more, how to say that, confidence.
So thank you. So another one related again. So for which optimization problem did you implement worm starting QAA, and how is the performance compared to ordinary or other variants of the QAOA?
So the beauty of what I'm doing is that I have no idea because I was just implementing this and Guoming is doing research. So I don't know. I don't know what problem he is. I mean, maybe I do know, maybe I don't know, but maybe I shouldn't talk about it publicly. So he is doing it for some problem and he decided that this method will be a good method for this particular problem. And I'm not sure whether he already started actually running any simulations or tests with that. But this is like important distinction between, like, I like this question because it shows the distinction between actually being a quantum software engineer and being a researcher. I just implement it, and now it's the work of the researcher to use it and just run it on 1 billion different problems, instances, and tell me whether its performance is good or bad. But like that's not my job to tell that. Like my job is to provide a code that allows them to run the experiments. Yeah.
Thank you. So I have another question, and I will send you the question also via the chat because it's a long one.
Sure.
So does your recent implementation on the worm starting QAA meet the conditions for providing quantum speedup that was recently published by a group in Los Alamos? Maybe you have seen it or not. I don't know.
I don't remember. I'm not sure what. I don't remember the paper that you are referring to. So I guess I can't answer the question.
Thank you. So I think that's it for the research-related one, and there are more general questions also. Mm-hmm. So a question is that I probably interpreted this as, so how does a quantum software engineer or a quantum software in general relates to the devices, and how do you make it device independent?
Oh, that's a good one. So, so on one hand, I will show you. So on one hand, the way we write software to make it device independent is that we have, again, an interface, so an abstract class called quantum backend, and any integration that we have, right, uses the same interface. So we have this run circuit and measure, and we have get expectation values, and for quantum simulator we have get wave function, and so on and so on. So we have a couple of methods that are same for each backend. So if, for example, we go to Zapata repo and we write QE forest, right? Or if we write QE Qiskit and we go into the simulator, we see that we have the implementation of, like, forest simulator. And here in the implementation of the specific methods, we just run, well, this is like forest code for running circuits, right? So we take this forest connection. On this connection, we translate circuit to pipepool, and then we basically run their code, right? And then we translate it to the same output as we are using in our framework. And basically the same is about Qiskit. So if you go to Qiskit and you select the backend, you just have regular, okay, so let's see where this is defined. Right, you have kind of Qiskit code for doing that. So I'm not very familiar with this code, but basically this like, oh, it's actually more involved than I suspected. Oh, but we have like we create like some IBM jobs, and we have job, execute, whatever there is, right? And the thing is that one way of doing this device independent is having these connectors, these interfaces. So, well, I can now just use my backend class, and as I have it defined here, right, I can run circuit and measure and get the results. And no matter which backend I'm using, I'm using the same format, and I'm getting, it's like uniform. So it's super convenient because it allows me to do later do stuff like, one moment. Okay, not here. So just going through the code base in the real time might be confusing, but I think we have it here. Okay, I will just backend. Okay, so then if we want to calculate estimate the expectation values or whatever, we can take the backend object and run circuits and then measure on this backend, right? So actually this code here is agnostic to what backend it's running on, as long as like the backend conforms. So I don't have absolutely any Qiskit or pipepool code or circ or whatever else code here in the logic that is about estimating the expectation values, because this is being done in the backend. So I separate my code like logically with respect to that. So that's a great thing. This is like one layer of making that device independent. And why I know it's a great thing, because we actually started long time ago. We had a code which wasn't like as separated, and we had a function like here. You would see 5 if statements for 5 different platforms that we had, and that wasn't either easy to use or debug or manage. So that's one layer. But the other is, well, you can only be device agnostic up to a point. So if you are running something on the real hardware, you right now with the NISC devices that we have, right now we just have to design our circuits in a way that's designed for a specific device usually, because the compilation of the gates alone just adds too much, overhead. So usually what you do is on what device you want to run your code, right? And then when you write a circuit for that, you just make sure that this circuit is compatible with this device, so that you don't, for example, use gates that you shouldn't, and you only connect the qubits that you should be able to connect, and things like this. So like on some level, it's device agnostic. On some level, you still need to kind of make sure that your circuit, that your code is actually written for a specific device.
Thank you. So I have another one question to you. So there's hope that quantum computing could find applications in finance and in banking and economics. So do you see anything? You can hear me, right? From the noise.
Can someone mute themselves? Or
it's myself.
Okay. I'm sorry. Then okay, that's good.
Yeah, I'm sorry.
Oh.
So there's hope that quantum computing could find applications in finance and banking. And from your experience, how close are we to seeing QC applied in finance and fintech industry? And are there any low-hanging fruits that we're close to getting? And also how we can, there's a second part of the question, so we can ask that later on.
Okay, so I answered this one. Well, I don't know, because I'm not working on anything finance related, and I just have no idea. And like finance is not really something of interest for me, so hard to say. And also the other thing is that actually it's, you know, like it's all speculation. I laugh that when I get into quantum computing about, yeah, I think about 3 years ago, people were saying that, well, quantum computers will be useful 2 to 5 years from now. And actually this haven't changed. So today people are also saying that they will be useful 2 to 5 years from now. And no, it's just super hard to say. So the like, not to leave you kind of with this non-answer, I think that we will see pretty soon some proof of concept solutions that could actually prove some advantage with the quantum algorithms versus the classical methods, but on the problems that are, you know, either too small, too big. So if you take a look at what Volkswagen did, so there's a couple of papers from Florian Neukart's group at Volkswagen. They spent a lot of time working with the logistics experts from like the transport experts to get to just like frame the problem in the right way and like define the problem properly and find the problem where quantum could help. And they took that and they combined it with their kind of expertise in the quantum computing optimization. And out of that, they came up with some interesting algorithms. But the problem is that these algorithms are not easy to generalize to be used in any other context than what they proposed, because there is so much assumptions and so much domain knowledge about the problem knowledge just like baked into the algorithm itself. And I think we can see things like this more like sooner, and this could be even production solutions. Like hard to say, like really, like I have no idea, but this is possible. Just the usefulness of that will be extremely limited to like this particular use case that they have in mind while designing the solutions. But this can also change pretty quickly given the rapid development. But that's like kind of how I like to look at kind of quantum computing being actually used for anything useful in the near term.
So thank you. There's also a second part of the question, which is that how could we go about building in-house software engineering expertise within quantum computing? Are there any work examples that you would point us to?
Okay, so the question is, I guess, what the we means here. So if the we is about individuals, then I guess just learning this and doing project and implementing papers, contributing to the open source is a great way to build like in-house, like your own kind of expertise within quantum computing. And we have a lot of examples of that at Quantum Open Source Foundation, QOSF, with the mentorship program and others. But actually probably in-house means in-house in some company, actually. So it's hard because it depends, like, okay, it depends on the company. Because if you are, it requires time and effort to do that. So if you are a small company and you just want to, be ready to use quantum computing, you might not have actually resources. You might not have enough people to allow a couple of people to just work on quantum computing projects for significant amount of time so that they gain this expertise, right? But if you are a huge corporation, well, you can easily allow for creating a quantum computing team within your organization that will be working on this type of POCs and projects. So, well, that's like on one perspective. But I think that the best way to get this expertise is to work. Okay, and I'm definitely might be biased here, but I think it's to work on the projects that are relevant to your industry and to the problems that you are working on kind of on a daily basis. And this is pretty uncontroversial, I guess. But the other thing is actually trying to get into partnership with some quantum computing companies and do a proof of concept project with them, because you can, like, it's, the field is really, like, this is really hard. Like, the quantum computing is really hard, and to get all the pieces right, it just takes a lot of time and effort. And trying to do all by yourself, if you don't have an in-house, like, very good expertise already, it just hard. It just takes a lot of time just to express your problem in the Ising-Hamiltonian terms, for example, right? Or figuring how to do that properly. So if you can partner with someone who actually knows the quantum part better, then you can work together on some proof of concept project, and then you will learn a lot about quantum computing in process, and especially about kind of the applied part, while at the same time the more quantum computing company will probably learn more about your domain, and they will be happy to just like learn how to apply quantum computing to this particular type of problems. Worthy examples. Oh my. So I would say that we had at Zapata, there was this paper that we did in cooperation with BP, and I know, like, we learned a lot, and I guess they also learned a lot in the process. So that's one example I can easily think of. I think what we did at BOR was also, before joining Zapata, I was working at BOR Technology, a startup, it's a very small startup, and we were basically trying to solve vehicle routing problem with quantum computing. So we had a pretty concrete problem with pretty concrete kind of constraints. And like we had like the problem was defined, and we knew that we don't want to try to solve all the variants of the problem, just like this specific variant. And then we just tried to figure out how to solve that. So just like focusing on a very specific problem and not trying to solve all the problem from the broader class or whatever. Just like take your assumptions, however realistic or unrealistic they are, just stick to them and don't bother about it, and just try to squeeze most out of that. Yeah.
Thank you. So I think that was all of the questions. So thank you for coming, and we will take a small break now, and thank you for coming again, and thanks for this great presentation and sharing your experiences with us.
My pleasure. And if anyone actually has any other questions that they will come up later, you can easily find me in the internet and just send me an email or message or whatever. I'll be happy to answer.
Thank you. So we will take a small break right now and then move on to Dr. David Lee.
Thank you very much. Have a nice day.
Have a nice day. Thanks for coming. Welcome back from our break, and now we will move on to our last speaker of the second day and in total. And the last speaker is going to be Dr. David Lee, giving us a speech on navigating Bloch surface with a single Xmon qubit. Before we start, I would like to introduce you to Dr. David Lee. Dr. Lee is managing the development of their university's control stack. Experimental speaking, he is taking care of the measurement part of every QC chip, while the design and the fabrication of the QC chips are taken care of by other team leaders. The whole QC development is happening in his teams in Academia Sinica. So welcome, Dr. David Lee. You're muted currently.
Hi, can you hear me?
Yeah, we can hear you right now.
Okay.
So, how are you today? First of all, before we start.
Yeah, a bit nervous, but okay.
If you want to, we can move on to the speech.
Yeah, sure. So should I share the screen now?
Okay.
Okay, hold shift. Wait a minute.
Meanwhile, maybe you can tell us about your work in Academia Sinica.
I'm working as a postdoctoral researcher here, and I am experimentalist by training. So I'm currently developing the measurement platform or the Qubit control or readout platform. So let's see, I get okay. I couldn't seem to share my screen. Do you see my screen?
No, we're not able to see your screen right now. Does it not allow it, or the option doesn't come up? Were you able to figure it out?
I'm not so sure because it keeps asking for permission, but I already granted.
Oh, okay. Let me ask the people how we can do it.
Okay, I saw it. Okay.
Okay, if you weren't able to manage it, you can mail it to us and then we can share the screen. If it is not possible for you to share it.
Okay, yeah. Okay. Sorry for the hold up. So do you see my screen now?
Yes, we can see the screen.
Okay, perfect. Okay, I guess I should just start now.
Yeah, good luck.
Hello, everyone. Thanks for inviting me to the speech today. I'm going to talk about how to navigate the Bloch surface with single Xmon qubit. If you think about it, we first discover at first we discover the integer. We have only 0 and 1. So in the later we also discover fraction, and then we also discover there's a negative numbers. So in the later on, we also discover something more exotic. It's called complex numbers. So we have this complex plane, and obviously there is some region between this opposite value, this 1 and -1. There's some space over here. that has some very interesting properties that we can explore. And let's say we have a sphere between this opposite. It doesn't necessarily be 1 and -1. It can be apple and orange, or it can be happy or sad. Let's say I want to reconcile this -1 and 1 with this -1 and 1. Obviously, both of these doesn't have the same meaning. So I have to reconcile it, and then I replace it in the happy or sad. And interestingly, we see that there's a superposition of the happy and sad over here. So this superposition is very intrinsic. It's a very intrinsic properties of quantum phenomena. And we can generalize all of these state into the single quantum state, which can be rewritten. And this quantum state is also happen to be a solution of the time-dependent Schrödinger equation. So in this solution, we have 2 parameters that we can use to navigate on this sphere. So for this field, we name it the Bloch sphere. And the Bloch sphere, we have the latitude and the longitude. So the latitude, so we have the theta is the angle over here, and the phi is actually the free evolution angles. And as you can see, this phi is actually omega t. So it actually depends on the time. So it evolutes all the time with a certain characteristic frequency. And this frequency is the resonance, is usually the resonance of the quantum object that we can use to lock onto the Bloch sphere so that we can do the navigation on the surface. So we can see that intrinsically it moves around and it's evolute all the time. So how do we lock onto this evolution? We use electromagnetic wave, and electromagnetic wave also is a solution of the Maxwell equation in such that the electric will induce the magnetic field, and magnetic field will induce the electric field, and so forth. And it will generate the light or electromagnetic wave in general. So this electromagnetic wave, it has also the same kind of complex characteristic that is very similar to the quantum. So with this frequency, we get microwave frequency, we can use it to lock onto the Bloch sphere so that we can observe our state and even manipulate the state on the Bloch sphere. That means we can go wherever we like to the surface on the Bloch sphere. So next we want to talk about which quantum object we are choosing for this experiment. And in this first 2 days, we have learned about the cold atom and the photonic system. So my focus here will be on the superconducting qubit. And it's not my place to comment on the other type of the platform, because superconducting qubit alone already has a large family to explore. Let's see the family here we have of the superconducting qubit. So over the years, the T1 and T2 keeps improving. The T1 has gone from just 1 nanosecond over here for Cooper pair up to the recently qubit used in IBM is almost approaching 100 microseconds over here. So the Xmon has improved from 10 microseconds to about 100 microseconds. That's the reason why we choose this Xmon. The Xmon seems to be a promising candidate for this superconducting qubit architecture. Of course, there's also other promising candidates like Fluxonia and the bosonic qubit later on, just discovered recently. And so now we want to dive into the superconducting qubit, especially for this Xmon. So first, I will start with the circuit design. As you can see here, we have 3 pillars: a circuit design, the chip fabrication, and qubit metrology. They all influence each other, and they all need feedback from each other. So before we design our circuit, we have to know our experimental result so that we can use those feedback to improve our design better. So to start with, we start from the Josephson junction. So this Josephson junction is you can view it as an oscillator, but it's not a harmonic oscillator. It's a nonlinear oscillator. Nonlinear means that the inductance is actually dependent on the phase difference across this junction. So in this Hamiltonian, you can view the first term as a kinetic term and the second term as a potential term. So in this case, we have the potential, which is a cosine rather than the quadratic form. So for this cosine, if we solve this Hamiltonian, we will have the energy spacing spread across, and this solution gives us one edge in which what's difference. The main difference between this nonlinear oscillator with the harmonic oscillator is that the spacing is not evenly distributed, and the difference between them is characterized by EC, the charging energy. So this charging energy, we also call it anharmonicity. So this anharmonicity is actually the one which gives us an edge for us to just focus on this 2-level system down here, so that we can use a unique frequency to just control a single isolated two-level system. Of course, in reality, it's not isolated. It's also influenced by the level which is higher, but that's fine. We can custom our circuit so that we also can custom our pulse setting so that we can avoid the excitation of the level which is above 1. And we design our circuit based on the junction area, and this junction area will decide what is the frequency, what is the intrinsic frequency of this Josephson junction. So now this Josephson junction is actually the core of our quantum object. This frequency gives the characteristic resonant frequency for our qubit. It will use this frequency later to excite, to manipulate our qubit, our transform qubit. And the other thing is that this resonance also will depends on the EJ. The EJ is actually the kinetic, the potential terms, and this EJ is actually characterized by the inductance across this junction. So if we have one junction, it's actually the frequency is actually fixed. That means you cannot adjust the frequency. So if we want to adjust the frequency, what we do is that we introduce a loop between the two junctions. We're forming the loop between these two junctions so that we can apply some flux between it, inside it, so that we can tune the frequency. So we can tune the frequency. In other words, we tune the phase difference across this both junction. So when we tune the frequency, we can tune from the lowest to the highest. So when the flux is zero flux, it will be at the highest point of the resonant frequency. When the flux is half of the flux quanta, theoretically, it will be at the lowest point, which is zero. But usually that will not be the case, since the both junction is not usually very symmetry. As you can see from this cartoon, the frequency can be tuned, and the two-level system spacing can be tuned by our magnetic flux. So with that, we have one element of our qubit completed. So with this element alone, the trick we do here is we introduce in another shunt capacitance over here. This shunt capacitance over here actually will lower the EC so that the kinetic term will disappear and just leave the term which is tunable by the magnetic flux and insensitive to the charge around it. So this way we can also reduce the anharmonicity. But if we want to observe this qubit, of course we can always observe it by directly measuring it. But the problem with direct measurement is that we will not read out the state that is the same as the state of the qubit at the time. So what we do is we take a sneak peek on this qubit with another component, and that component is our harmonic oscillator or the superconducting resonator. And this superconducting resonator is designed such a way that the resonant frequency is detuned. It's not far detuned, but largely detuned, so that the detuning will be much larger than the coupling between this qubit and the cavity. So if we do this detune, that means we only slightly entangle this cavity with the qubit instead of strongly entangle them. So in this way, we can take a sneak peek on our qubit state through the cavity resonator. So this cavity will serve as our eyes and ears. So with this Hamiltonian, the omega q here is actually the qubit, is our qubit frequency. Omega c here is our cavity frequency. And from this Hamiltonian, we can see that when this qubit and the cavity is slightly entangled to each other, instead of a strong coupling like the maximum entanglement, we have a very weak coupling, and this coupling along with this detuning will give up some shift, and this shift is called a dispersive shift. We use this shift to detect the qubit state, whether it's in 1 or 0 state. And how we do it is rather not straightforward, as if we plot the frequency and the power or number of photon and we pump into this cavity, because only through this photon we pump into this cavity, and then when the photon get out, we will know the state of the qubit through the state of this photon. So in this state of the photon will depend on the qubit state characterized by this dispersive shift. So as high power, in high power means that the N is larger than the ratio of the detuning and the coupling square. And this is actually 4 times the critical photon. So if this n is too large, we kind of saturate this cavity so that it will not see the qubit anymore. It cannot see the cavity since there's thousands of photons inside. It's usually thousands of photons inside this cavity, so that the cavity cannot see the qubit. So if we want to see the qubit, we have to lower down the power to the critical level. The critical is defined, the critical photon number is defined as the quarter of this square of the ratio between the detuning and the coupling. So if we hit this critical level, our resonant frequency will do some shift. And this shift is rather tricky. This shift is given by chi 01. It's not yet chi that we want to use it to discriminate between 0 and 1. It's just chi 01 means that at least you know where is your ground state is. So we can safely denote this as a ground state because we didn't excite it yet. It's just in the temperature bath that allow it to be in the ground state. By the way, our temperature is 10 millikelvin. So in this temperature, there's no excitation available to excite this qubit. So we can assume that this qubit is always in the ground state. So if we further lower the photon down to almost the single level, we can do some interesting things that we can observe 0 and 1. So the 1 and the 0, or the ground state and the excited state, if we view it from the perspective of the cavity. So the thing is that if we know this chi, we can find a region where it is most sensitive to the phase of the cavity. So the phase of the cavity will be highly dependent on the state at this cavity frequency. So at low enough power, if we probe it on this frequency, we can see the phase shift when it is excited from 0 and 1. Now we have all the elements we need, the cavity, the qubit. We can start to construct our circuit, which we may use to manipulate and read out our qubit. And we put our qubit, we put our Xmon qubit on the chip made on a sapphire substrate, and we have the readout line over here. The readout line here is where we pump the readout photons here to detect the state of the qubit. And we use the lambda over 4, the quarter wavelength CPW cavity, as our readout cavity. And we have the aluminum ground plane over here. All of the substances used here is aluminum. And we can zoom in the qubit part. So this is our Xmon qubit. Because this Xmon has a cross couple, it uses the cross as a shunt capacitance. So we also call it Xmon. So we have this, we have all the elements that we want. We have the readout line over here, and we have the cavity, and this cavity is coupled to our qubit. And we can continue to zoom in to see our qubit. This is the loop that we were talking about, the loop where we apply the magnetic flux to tune the qubit frequency, and we zoom in enough, we will see the junction. And this junction is the one which decides the resonant frequency of the qubit. And this junction is fabricated in our clean room using the e-beam evaporator. So now I will briefly talk through the chip fabrication. So our chip is first coating with the RP resist and spin coating with the RP resist, and then we develop it to write the pattern and then develop it to expose the substrate below. And after we expose the substrate below, we can deposit our aluminum on top. And after deposit the aluminum on top, we have the circuit completed, and we can lift off the unwanted area so that we have the complete device ready for our measurement. And how the aluminum tunnel junction is fabricated is using the shadow evaporation method, where you shifted the angle to make junction. As you can see from this AFM picture, that's the device is very well fabricated. The thickness is quite uniform, and yeah. So this is the two-angle deposition. You can see that the quality of the junction is quite good. When we zoom in, the quality of the junction is quite smooth. The only problem with this fabrication is that we use the same angle for two-step evaporation. So it will introduce some unwanted oxide layer that may influence our coherence time of our qubit that we will see later on. And the new design is we already employ the different angle for different stage of evaporation. In this case, it has a 90-degree difference. And the quality is quite impeccable. So in this 90-degree, there is no redundant rush area junction. So this is probably a potential source of our decoherence. Next, we move to our measurement part. And this is our dilution refrigerator here in Academia Sinica. And we have a measurement rack over here, which measure our qubit at the base temperature, which is usually under 20 millikelvin. And when we open up the dilution, we can see there's a lot of coaxial cable down here. And this is the full view of our rack, but it's improved a lot now. This is last year photo. And down here at this is the mixing chamber. Neat mixing chamber is where the 10 millikelvin will be, and where we will install our device here. So our device will hook up with the coaxial cable, and this coaxial cable would go all the way from the millikelvin to the room temperature. When we zoom in on this part, the chip is located inside this sample holder and is wire bonded. So now we look at how we measure the cavity. First, we want to know our eyes and ears is okay, so that we can continue to observe further the qubit state. So it's very important to characterize the cavity before that. As you can see, the background is red. That means it's very hot. It's very hot for our qubit. It's at room temperature. So when we go down to 4, it gets a bit colder, and 1 Kelvin is even colder. And next we move to the 100 millikelvin, which is called the cold plate. And under this cold plate, we will further go down to the 10 millikelvin, and this 10 millikelvin machine chamber is where we install our qubit. And this attenuator will go through the readout line, and this readout line will be coupled to the cavity in a notch type coupling. So this cavity in turn coupled with this Xmon qubit. This way we can measure it so if we pump the signal from the network analyzer here, it will go from room temperature and then with a series of attenuation to get rid of the thermal noise, so that when it reaches the millikelvin temperature, is only a few thousand photons. So as you can see, the total attenuation here is about 66 dB, but when we include the attenuation of the cable, it will be roughly 80 dB. So when the photon is down here, it will interact with this cavity, and then this cavity will give out the photon that will inform us the state of this Xmon. And this take note that the photon coming out of this cavity is rather feeble because it's at a resonance state. That means the part of the photon is absorbed and only a few will come out. And that's why we need the amplifier at the 4K stage. We install the amplifier at the 4K stage because it has a lower noise temperature. Means it will introduce less noise to our upcoming signal. And we also install another low noise, about 1.7 dB low noise amplifier, and then back to our network analyzer to analyze our cavity response. So when doing the measurement, we will get the data, and we want to know how to characterize the notch type cavities. So we have the meandering cavity over here, and this tree cavity is deliberately designed so that they have a different frequency. It's like a telephone number. It has a different telephone number we can tune in to see our state, our respective qubit state. So first, we have this type of resonance response, and from this resonance response, we can do some fitting to get the Q of our resonance. So after fitting this Q, we will know the intrinsic coupling, the intrinsic Q also. This intrinsic Q is the one who will determine the coherence of our qubit in a way. So with this, if we know the couple and the loaded Q, we will know the loading factor. The loading factor is simply the ratio of this couple to the loading Q. Is the QC over QL. We will get a loading factor. Loading factor means that how much the photon pumping here will be absorbed by this cavity. So with this loading factor, we can easily calculate the power arrived at this cavity. And using this power, we can determine, using the single photon, we can you can calculate the corresponding single photon power limit. Means that when you apply this power, you can be sure that there is just about a photon which will eventually reach our cavity, as illustrated by this cartoon. So we also have to choose the right readout point. How we choose it is that we pick the readout frequency so that it is the most sensitive to our qubit state. So as previously mentioned, the flux can tune the qubit frequency, and this qubit frequency will affect the detuning, and this detuning will also affect the dispersion shift. And this is the bare cavity over here, and this is the shifted cavity over here. So this shift is totally dependent on the flux that we apply. So if we take a look on this curve, so this is the SY frequency. SY frequency is corresponding is the frequency that we use to search for our qubit frequency. And this is the readout frequency. The readout frequency is the one we use to see the qubit state. And we want to choose the readout frequency so that the qubit frequency is always consistent. So this is the area where the qubit frequency all is consistent. And also the area over here is also all consistent qubit frequency. We want to avoid the region between these two. And how to avoid that? We have some simple rules. And the rule is that we tune to the zero flux so that we have the maximum dispersion shift. So this maximum dispersion shift will give a guideline on where we should measure our qubit state. So it's totally confined here. So the thing is that if we halfway through this region is the best readout region. So this is the right area, and the center one is the forbidden area because it will give you the inconsistent qubit frequency. And the qubit response is also very subtle. As you can see from this cavity resonant response here, the red is when the qubit is not excited, means the SY frequency is not aligned with our qubit resonant frequency. It will show the usual resonant response. And when the qubit frequency is right, the cavity response will also shift, but it's shifted in a very subtle way. This region here is the region over here, and this region here is the region over here. And this discrepancy is the one we use to detect our qubit signal. And this give us the qubit frequency. And we also observe that there's some gap between this tip and this gap is our enharmonicity. So how we get the qubit resonance for every flux. So this is the single photon limit, and this is the critical photon limit. As we mentioned earlier, between this one is most qubit state sensitive. So we want to use the power over here to observe our qubit, to detect our qubit, or to find our qubit resonance frequency. So when we apply a different flux, we can tune the qubit frequency. So as you can see, the signal is very feeble, so that one usually need to normalize it to see. But for this picture, I didn't normalize it, but we can see clearly the trend of the changing qubit frequency with our applied magnetic flux through the loop. And this is the dispersion shift moderated by our flux current. And this point here is at the larger the frequency, the bigger the shift. So the shift over here will correspond to the highest qubit frequency over here. And this is where the flux is exactly the half quanta, because it has the lowest shift, it has almost no shift. Means the qubit frequency is either very low or almost zero, so that it will not have any dispersion shift. So from this picture, we see the gap here. I didn't fully explain what the relationship of this gap with the anharmonicity. This gap here is actually the half of our anharmonicity. So if we view the qubit diagram here, we have the state 0 for the qubit, and then the 1 and 2 and 3. So if we pump the frequency, that is the same as the F1, it will excite the 0 from the 1. If the same is true for F1, 2 and F2, 3. So this F01 is the square root of 8 EJ EC minus EC. If we pump 2 photons, and then these 2 photons, if the 2 photons is excite the qubit directly from 0 to the 2, that's why we see the second line here. If we have 3 photons, you will see the third line, and 4 photons with the fourth line, and so on and so forth. If your power is going higher and higher, that's the way usually people use to characterize how many photons they apply to the qubit. And in this simple derivation, we can see that this F01 and this F2P is actually the gap that we measure. So this gap times 2 is our anharmonicity. We characterize the anharmonicity this way. This anharmonicity is important for us to know the chi that we mentioned earlier. The chi is the one we use to discriminate the 0 and 1 state. So this is the gap corresponding to these differences. Okay, now we move on to how we control the qubit state. So we have established that the Xmon qubit will be our quantum object, where it can represent the Bloch sphere. So that means when we apply some pulses to this qubit will have to respond and in the similar manner of the Bloch sphere. In our qubit, we have the XY line and the Z line. So if we apply some pulses to our Z line, the duration of the pulses will determine how much is evolutes along the Z axis, as you saw earlier in the animation. And if we apply the XY gate over here near the cross here, and this will excite, depends on the X or Y. If we use X, it will rotate the Bloch sphere. Actually, it will rotate the qubit state over here. So initially, you can think of initially the qubit state is at the 1. So when you apply the pulses, this state will move along the qubit, the Bloch sphere, if it is not decay or decoherence. If it is still in the pure state, the surface of the Bloch sphere is actually representing the pure state of the qubit state. When it decays, it will move inside the Bloch sphere. So if we, same way, if we apply the Y here, we will expect the we will expect the qubit state represented by the vector here will move around this y-axis. So how far, how much they move around here is totally depends on the duration. On both the duration is actually on both the duration of your pulses and also the amplitude of your pulses. And this, how long and how high we need for the pulses to control the full circle is actually determined by our Rabi frequency. This Rabi frequency is totally dependent on the GSY, which is another coupling between this driving line and the cross over here. This is a good way to characterize how much coupling that we need, so that is within our dynamic range of our measurement system. As you can see that in this Rabi oscillation, we apply the first we already know how to read out. We choose the right cavity frequency, we choose the right power, and then we apply the pulses before that. What we do in this scheme is the sequential pulse scheme. That means the readout pulse is applied after we drive the qubit. So if we continuously drive the qubit after a different time, we read out, we will supposedly get an oscillation between 0 and 1. So in this case, for the ideally on resonance, that means it is zero detune. This is not the one we want, because at 0 pulses, we get something between 0 and 1 is not totally ground state. So this method is demolition method. Means the qubit state that we read out will always deviate a lot from the prepared state. What we want to do is non-demolition. This non-demolition will align well with our qubit state. As you can see, when we give a 0 duration, it will have it will correspond to the ground state instead of the superposition state. So this curve just shows that if the power is high enough, when the driving power is high enough, you can usually use this power to adjust the Rabi frequency. And in reality, it will not always oscillate. It will decay at some point. And this decay will determine our T1 and T2. But from Rabi oscillation alone, we cannot determine T1 and T2 separately. It's rather a complicated combination of both. So this just shows that in our experiment. So now we want to apply this scheme to our real qubit that we just fabricated. So we have the SY pulse applying before and after each duration. We immediately apply a readout pulse so that we will know whether it's in 0 or 1. And take note that the 0 and 1 is the average expectation. It's not the current state. It's average over the any ensemble. And this is our qubit performance. So as you can see, for these qubit devices, it decay about after 1 microsecond. So this corresponds to the early days of when transport is first discovered. And we also tune the SY frequency. So if it is the legit Rabi oscillation, we should also see some detuning effect on the Rabi oscillation. So if the XY frequency is a bit detuned from the right qubit frequency, the Rabi oscillation will also become faster, but it will not completely drive the qubit. Means that it will not completely go to the excited state. That's why you see the signal here is rather feeble. This is a good way to recalibrate our qubit frequency to a higher precision. So for this sample, at 0 flux, we get the qubit frequency of about 5.94 gigahertz. And now we want to measure the T1. What we do is that we apply a pi pulse here. After we apply the pi pulse, we apply some delay. That means we didn't apply anything for an amount of time. And we measure the state of the qubit with the delay. So you will see that when we drive the pi pulse, supposedly the qubit will be pumped from 0 state to the 1 state. And after it stays at the 1 state, after some delay, the state will decay. And this decay will pick up by these readout pulses that we can measure and see how the qubit decay. And in our device, we found that the decay for this qubit is around 1.03 microsecond, which is our T1. So for the first try is quite successful, and we want to improve that further. And we also want to see the T2. So the T2 is just another way to improve the qubit frequency detection. First, we apply the pi over 2 pulse. Well, when we apply a pi over 2 pulse, we move the state from the Z axis to the X axis. And from this axis, as I mentioned at a very early stage of my presentation, this equator here is where the qubit do the free evolution here. So what we do is we apply we apply a delay, and then to let the qubit evolve. And since our measurement basis is along the Z axis, if we apply the readout pulse right after this, we always get the same expectation. So we cannot see it evolve freely. What we did is that we move the measurement basis to the X axis. How can we achieve that? Is that we apply another pi pulse. We apply another pi over 2 pulse, so that it shifted. And the rotation basis is just relative to this Bloch sphere. That means if we drive the Bloch sphere clockwise, our measurement basis will rotate anti-clockwise and vice versa. And these techniques will be later on used for calculating the expectation value for each component of the Bloch sphere, and is a powerful tool. So as I play the cartoon over here, you can see that along the delay, it will feed evolution. But the problem in reality is that it will not always stay on the surface. Eventually, it will soar deep into the center and decohere. And this way, we can characterize our T2 by taking almost 1/3 of the decay. And if we get this T2, we can easily get the T5. The T5 is actually the defacing time. Defacing means that the qubit frequency uncertainty. So the qubit frequency is not always the lock on the certain frequency. The frequency will always fluctuate a bit. So using this method, we can even measure the uncertainty in the qubit frequency. So theoretically, if the frequency is absolutely stable, we will not have T5. So if we will not have T5, our T2 will be exactly twice the T1, but that doesn't happen. Usually for most systems, the T1 and T2 is almost on the same order. So now we measure the T2 on this qubit. So as you can see here, the black line here is the one when we are zero detuned. So this is an even better way to recalibrate our frequency to a much higher precision. So when it's detuned a bit, we can already solve the oscillation. And this oscillation is very well corresponding to the detuning of the applied SY frequency from our qubit. So this way we can get the right frequency. And this is important for our later gate application, because when we apply a gate, we want the frequency to be as more detuned as possible from the qubit frequency. So for this sample, we get the dephasing time of about 600 nanoseconds, and T2 is almost is about 460 nanoseconds. It's half of our T1. And it is expected, because if the dephasing time is this low, we will expect some frequency instability. As you can see from this curve, is always fleeting. So we cannot get perfect Ramsey fringes over here. That means we have to do some improvement to our circuit. So what we figure out is that our 3 qubits are probably too close together, because I found out that when I apply the SY pulse over here, I can always measure the Rabi oscillation of this qubit and this qubit. And this is not good for the decoherence. It is good for control, but it is not good for decoherence, because this will limit our decoherence. And what we do in our next version, we want to move this far apart. So in our second version of the Xmon qubit, we move them far apart. And we also design some flux trap along this, so that the flux, some stray flux will be trapped inside, and this will even reduce the crosstalk between this qubit, and also stabilize the flux applied to the qubit. So there is some improvement made to this chip. First is far more apart, and the second is that we have the flux trap. And yeah, also the third improvement is that for this chip, the junction is not a single angle. It has the right angle deposition. So you got a very nice pure junction over here with no stray large capacitance junction. So this is more straightforward to our modeling. So this will also contribute a lot. So for this version of our chip, we improve a lot of things at the same time. So we should see some improved result. So this is the improved coherence that we get by almost 1 order of magnitude. And instead of just 1 microsecond, the T1 for this sample already improved to almost 10 microseconds. So if you look on this curve, the blue line is the T1. So the T1 here is about 15 microseconds by doing the fitting, and we get the T2 of about 10.5 microseconds. So from this 15 and 10.5 microseconds, we can easily calculate the defacing time. So for this sample is very much improved, because this is the first time the defacing time exceeds both T1 and T2, and this is a good sign because we have the right direction. And this is an amazing calibration of our qubit frequency. So the period of the x-axis is always a Fourier transform of the period of the value of the y-axis, and vice versa. The period of the y-axis is the Fourier transform of the value of the x-axis. But for the x-axis, we have to be careful because we want to take the detuning and not the absolute qubit frequency. So now we have characterized our T2. Then we move on to apply the X and Y gate independently. What we do earlier is that our X and Y gate is not well defined, because we apply the pulses at the I and Q at the same time. But for this experiment, we will individually apply the S gate and the Y gate through the I and Q respectively. So the S gate is just this is the method of choice. Conventionally, one map the X with the I and the Y with the Q. You can also do it inversely, Q with the X and I with the Y. It's okay. You will get the same result. So this way, we have the tool to manipulate, to drive our qubit on the x-axis or the y-axis. So now, if we view from top of the block of our Bloch sphere, this is the top. This is the pointing up of the z-axis, and this is the x-axis, and this is the y-axis. And if we apply the XY gate, what we can do is we can navigate through along any surface on this Bloch sphere as we wanted. So if we map our control X and Y, and for these purposes, we usually fix our duration. And in this experiment, we fixed the duration at the 100 of nanosecond. We fixed at that duration, and we change the amplitude. And we change the amplitude. We also change the Rabi frequency of the qubit. And this way we can actually, with the fixed pulse duration, when we change the amplitude, we actually can decide whether it is rotate at pi/2 or pi or 1.5 pi. And this way we can use this IQ as our compass to see where we are on the Bloch sphere. So what we do is that we using this IQ to lock on our basis. So this method, we use this method to rotate our measurement basis. So when we apply along this Q, we actually, when we increase the Q amplitude from 0 to the 3 power over 2, what we did is that, remember that the readout, the initial measurement basis is along the z-axis, so that this measurement axis is actually vertical down. So when we apply, we will change this Q. What we do is actually we move the measurement basis along the line of the x, y, or minus x or minus y. Let's say we apply nothing at the x, but we apply some pulses at the y, and then we vary the amplitude so that we can drive the qubit. At the same, if we view from the measurement basis point of view, because the measurement basis is oppositely relative, the rotation oppositely relative to our driving, we can view that the measurement basis move the bright part, the top part, because for our measurement, the bright spot usually is corresponding to our 0 state, and the dark spot is usually corresponding to our 1 state. So if we lock if we apply this way, we actually lock the bright spot with our y rotation. And if we do the same thing at the x, we didn't apply any pulses on the y but we apply the I amplitude, which is on the x. So this way we can move along the x-axis so that the bright spot is, the measurement basis is moving toward this part. So this is a good way to lock onto the Bloch sphere. So that means if your state, the bright spot always follow your quantum state. We can also do it oppositely. So we just turn the Bloch sphere 180 degree, or conversely we turn the IQ 180 degree. It is the same. So in this case, if our compass is aligned with this 180 inverse Bloch sphere, what we lock is not the bright spot. What we lock is the dark spot. So whenever the location of our qubit state is, the dark spot will always be there. So the dark spot will always follow the qubit state. So if let's say when we measure this I and Q, and then we get the intensity of our readout across this 2D dimension, if the dark spot happen to be here, that means the qubit state is on this part of the Bloch sphere. And this is called Wigner tomography. And first we apply the pi pulse. We prepare our state by applying the pi pulse so that the state will move from 0 to the 1. So as you can see, there's a dark spot at the center. That means it's pointed downward. So we can know that the state is at the 1. And then we prepare it. If we prepare it at this 0 plus 1 state by applying the Y gate by minus 90 degree, we observe that this is a matter of choice. But for now, if we focus on the bright spot, if we view it from this side, so the bright spot, if the view from the top Bloch sphere, but you view it from this side, you're sitting here, and then you observe it down on the Bloch sphere surface. So you see that if this bright spot is on here, this means it's in the state, and it is quite aligned with our preparation. So if we prepare at the X, if we apply the X rotation from minus 90 degrees, so that the state will put along this line such that the state is at 0 plus I 1. So as you can see, if you follow the dark spot, yeah, it corresponds rightly on the Bloch sphere here. And also if we apply nothing or apply 360 degrees, we get back the bright spot at the center, which means the 0 state. So these two is stark, has a stark difference for you to differentiate between the 0 state and the 1 state. And when we move, when we rotate Y at the 90 degree, also you can see that it's opposite with the minus degree. So when you view it from here, so when you view it from here, the bottom one will correspond to this part. So it's quite aligned. And also the same with this. If you view it from here, the bright spot will correspond to this one. And yeah, the dark spot is more straightforward. The dark spot is you view it from here, and on the top Bloch sphere you view it from here. So it's quite straightforward in this presentation. So this corresponds to the lower part, this corresponds to the upper part, and this also, and the same is true for this. And I also do some exotic rotation. For this rotation, I rotate X 90 degree. This means the state here, I first rotate X 45 degree. So if I rotate the X 45 degree along this X-axis, I rotate it 45 degree over here. And then after apply 45 degree, I apply the Y 90 degree. So when it's over here, when we apply the Y 90 degree, it will go from here to here. And as you can see, the dark spot, when we view from here, is almost 45 degree over here, rightly correspond to our where the Qubit state is. So now we have successfully navigate on the Bloch sphere, and we can do further measurement, but that is for the future measurement, because this measurement will need a higher fidelity. But what I can show you is how we will do the quantum state tomography. What we do is we measure each component, each vector component of the Bloch sphere. So if we want to measure the Y component of the Bloch sphere, we apply the pi/2 rotation on the Y-axis, and then measure the expectation. And then for this state tomography, we don't want to measure the expectation. Instead, we want to measure the eigenvalue. So this will achieve by the single shot measurement. So the single shot measurement will be performed on these 3 spots. This is correspond to the Y component. This will correspond to the X component. And this right here on the center one is correspond to the Z component. So for each of these components, if we measure the one-shot measurement, we will get the eigenvalue of that component. And when we apply this eigenvalue, this eigenvalue is actually, we can compose this eigenvalue to form a vector. This vector times each of the Pauli matrices and plus the identity matrix, we will get the density matrix. And this way we will get our quantum state tomography. So this Wigner tomography also has this happen to be look the same as the recently discovered, recently observed black hole, the supermassive black hole, just recently by the EHT. And now I want to take some time to introduce our equipment. We have a class 1000 clean room to fabricate our superconducting qubit. And this is our SEM. This is our yellow room. And this is our evaporator over here, where we deposit our superconducting aluminum on our chip. And we just recently procured a new SEM with a much higher resolution, so that we can get a good feedback on how good is our Josephson junction. And we also procure another new evaporator. And this new evaporator give us an advantage to do the in situ fabrication. Means that the sample will not get into contact with the air. Is right from the start and to the finish of the evaporation. And this evaporator have many functions attached to it. All the process will be done in situ and transferred to the evaporator over here. We have RIE attached over here, and annealing also, and oxidation, and all the function that we need is in one place, so that it will reduce the unwanted oxidation to our junction. And we also have just procured a new dilution fridge unit. So it just installed this much. And the cooling power is about 400 microwatt is the basic one. So we have the 22 input coaxial cable here. And we assign the first dilution for the 1Q chip measurement to improve our coherence, fidelity, and the gate. And for the dilution B, we will be dedicating the measurement to the 2 qubit chip for the gate connectivity, and also the two qubit gate fidelity, and so on. Okay, apology. The first dilution is both 1Q and 2Q, and the second dilution is totally for 2Q. And we have a 2 output line here, means that we can do a 2 simultaneous measurement on 2 samples per dilution unit. It will give us the high measurement throughput, so that we can give a much more quicker feedback to our fabrication. And this is our long-term 1Q measurement. Here we have a high resolution Tektronix AWG here. We also the vertical resolution and the horizontal resolution is both very high. And we have also a very high digitizer over here. This whole system is dedicated for just 1 qubit, but we want to scale it up. So what we do is, instead of the bulky equipment, we will we will change into the modular one. So we have a modular ADC, modular local oscillator, modular the AWG. So AWG is here, the digitizer is here, ADC and the DAC. So the DAC will send the control pulse and the readout pulse inside the Qubit chip and getting the signal out and digitize it over here. And all of this have to be done simultaneously, so it has to be well synchronized. So the FPGA is used to synchronize better of our each module. So this is our way of doing the measurement to distinguish between 1, 0, and 1. And this is our new. It has to arrive more unit, but this is the first unit that we have procured. And as you can see, this is our new direction. So a bit of promotion here. We also have a new base in 2 years. So the base will be larger, will be dedicated for quantum research. So it is the National Quantum Research Base. It will be based in Tainan. So the Qubit measurement facility will be located over here. So it will house a lot of dilution over here, and it has also we will also have a larger clean room for Qubit device fabrication. So the projected finish date is about 2022 July, and so we will have the research on the quantum computer, quantum materials, quantum optics, and also quantum cryptography. So it's all dedicated to the quantum research. Okay, so we are hiring now for the quantum computer project. We need some talents to design the multiple qubit connectivity, to set up the measurement, to construct the firmware architecture, to design the parametric amplifier. Yeah, this parametric amplifier is very important because we don't. This will improve our fidelity by orders of magnitude, and we also need some talents to fabricate both qubit and parametric amplifier to investigate through the decoherence and dephasing issue. And also for the future is to design the 3D chip packaging so that you can scale up the qubit numbers. And for this national quantum research base, we also need some technicians to take care of the clean room and fabrication equipment, and also the lab manager, and also when we get to about 7 to 8 qubit, we will put our qubit on the cloud. So we also need some software engineers to build up the cloud platform. Okay, now I want to thank a few people, and this project is led by our principal investigator, Professor Chi-Tong Chen, and the circuit is designed by Jeremy and Jing Chia, and chip fabrication is performed by Lance Lee and Xiao Chen, and this qubit maturity is performed by me, and we also have the equipment upkeep by Zhe Yan. So we want to thank you guys, because without you guys, it's not possible to have such achievement. So we have a long way ahead, and we are just getting started. So, and I want to give my appreciation and many others also, which is not included in this slide. So, thank you. And I conclude my thoughts here.
Thank you, Dr. Levy, for this amazing speech. So if you have time, we have some questions from our viewers.
Sure.
Okay, so the first one is someone asked that if there's a website link for the job opening, if you can send us through that through Zoom, we can share with it.
Oh, yeah. Yeah. Link. You can drop me. You can drop your resume or CV to my mailbox. Yeah. Okay, you can find my mailbox inside this web page. This is our group web page over here.
I think so. There's another question that asks, what is the difference in the nib design other than the angles?
You mean the fabrication angles, the deposition angles?
I don't know. That's a question from a viewer.
Let me see. The angle difference is 90 degrees. So for the first version, we deposit different layer. So for a different layer, we use the same angle, so that our junction that we obtain is always largely overlap. Of course, we will have our junction here, but it will instead of this, it will overlap in this direction. So we have a very large capacitance over here, and this large capacitor may or may not have some effect on our qubit performance, but based on the result that we get, it does improve significantly. Yeah. Does that answer your question?
I hope they did.
Okay.
So someone asked that what was the most challenging part to develop QC's control stack system?
The most
difficult part.
Oh, okay. The calibration part. Because we have to, okay, this is a very good question. Because we have to make our S gate and Y gate as precisely as possible. So what we do is that we have to calibrate it. We have to calibrate so that we don't allow another frequency to mix with the qubit frequency. So we calibrate in such a way that the leakage is low, the leakage for the carrier leakage, and also the mirror leakage. And we also want to see the IQ balance is perfectly balanced. As you can see from this slide, and this is a well-calibrated one. This is also a very well-calibrated one. But if you notice carefully, this is not that well-calibrated. And for the Y part, for some reason, we still have some work to do on the calibration. So we need, we usually use some high frequency scope to do that kind of measurement, to do that kind of calibration. Yeah. And another thing about calibration is that calibration itself also is an optimization process. So if we get more and more qubit, the calibration will be more and more tedious, and it will take a lot of time. It will take a lot more resource, computing resource, and it's kind of ironic that we also use QC to do optimization. So for the initial part, we will use AI to do the calibration, and then we will achieve quantum algorithm that we want. Maybe in the future, when that optimization is matured, it can optimize back our more basic control calibration. Yeah, I think that's the answer.
That answers it. Thank you. So, someone asked, is this related to somehow with the CMOS technology in transmon qubits or not?
Again?
Is this related to CMOS technology with transmon qubits or not?
Oh, yeah. Okay. One thing I forgot to mention is that for this first version, we use sapphire substrate, but we want to be aligned with the CMOS verification flow. So for the second version, we actually use silicon as our substrate. So this will align much better with the CMOS technology. And we also have some collaboration, also have some many more projects, which we will develop some cryo CMOS, which will be installed on the 4K plate. And we also will develop CMOS for parametric amplifier. And the good news from this result is that even if we change from sapphire substrate, which has a lower loss compared to the silicon in terms of dielectric loss, we managed to improve our T1 and T2. So this will be a good indication that silicon substrate is working. So it will be aligned with the CMOS technology. Yeah, that will be my answer.
Thank you. Someone asked that what's the difference with XY and Z gating? They said you applied pulses to XY line and controlled Z parameter and the qubit state in the Bloch sphere. Is Bloch sphere control is irrespective of gating?
Okay, very good question. And yeah, for this, I focus more on the SY gate rather than the Z gate. The SY gate here is actually the pulses modulated by the qubit evolution frequency or qubit resonance frequency. And this can only rotate the X and Y direction. But if we want to rotate the Z axis, what we do is that we apply some pulses, and that pulses is DC pulses. It's not the RF pulses. So these DC pulses will increase the flux for a very short time. Will increase the flux for a very short time, so that it will tune away the qubit frequency. That means if you apply a short period of flux, a different flux to the qubit will experience a shift of the qubit frequency. That way, you can view the Bloch sphere slowing down or speed up, and that differences when it speed up or slow down, that differences frequency. That difference in frequency times the pulse period will be the 5 degree that you will get. And this way we can achieve the G-gate control. I hope that answers your question.
You. So someone said that Qubit basis measurements and Z bases are perfect with matrix theory calculations, but X and Y basis measurements are not. So matching with theoretically matrix measurements or operator calculations. So they ask why that is.
Okay, this question is a bit complicated. May I listen to the question again?
Okay.
Or where can I see the chat?
To the chat too. So I have sent you the question again. The question is Qubit-based measurements and Z bases are perfect with matrix theory calculations, but X and Y basis measurements are not so matching with theoretically matrix measurement operator calculations. So why is that?
X and Y basis measurement are not so matching with theoretically matrix measurement operator. Okay, I will answer this in the perspective of an experimentalist because I'm not a theorist. And what I can say is that the G basis measurement is the most straightforward one, because whenever you send a readout pulse and you get the response, you will always get the distribution between the 0 and the 1. But for the X and Y basis measurement, is rather tricky because that you have to precisely turn your basis measurement to the right X basis, because a slightly difference will give a readout errors. So yeah, in a way, X and Y bases are much trickier than the Z bases. I hope that answer your question, because I'm not so familiar with the theoretical part. I'm
Thank you.
most familiar with the experiment part.
Someone asked how to apply measurement pulse for a single shot readout, and also how you can count the number of shots.
Okay, good question. Okay, yeah, I didn't explicitly talk about how we measure the single shot because we didn't achieve the fidelity that we wanted. But I can briefly describe it, how we do the single shot measurement. Okay, for this pulse example, and this we for a single shot measurement, for every shot, we integrate the readout pulse response along the time. So if we integrate it, like say a few microseconds at the later part of the pulses, because we find that it need the cavity requires some time to output the photon that will reflect the qubit state, and that time is usually proportional inversely proportional to our Q load. So, okay, apology. Is directly proportional to the Q load. The much better the Q, the longer the time we need to get one photon out to read our state. When we get a photon out for a period of the cavity decay time, we start to integrate for a few microseconds. So every integration will give you 1 point on the short measurement, and we do it 1,000 of times or even 10,000 of times to get a distribution. I hope that answers your question, because we usually apply this pulse for many shots. This is just a single instances. We have many pulse repeated over and over again, and then we get the statistic out of the response. Yeah, I hope that's the answer that you want.
Thank you. I don't think there's any more questions coming, so I want to thank you for coming and giving us this very informative presentation.
Okay. Yeah, thanks for the invitation. It's been a great pleasure to give a talk, to introduce our group and result. And like I said, we are just getting started, and we will have more exciting results following this. So we have many projects, and we will scale up our qubit year by year. Yeah. So thank you again, and try to keep in touch.
Thank you. It was a really comprehensive presentation for us, and it was nice to understand and see the insides of the implementation and the hardware side.
Yeah.
So thanks for coming again.
Yeah, thank you.
For the people on YouTube watching right now, we thank you all for coming also and listening to these 2 days of great talks. We are finishing up, and we would like to inform that if you have filled at least 4 of the attendance forms that were sent to the YouTube comment section, you will be given a certificate. It will be prepared and it will be sent to your email that you have provided to us. Again, thanks for coming and listening to these great presentations from great speakers. So I thank you all for coming again, and see you soon.